to Sleepy Facts with Justin. Tonight, we are going to travel somewhere very old, somewhere quiet and vast and still. We are going to travel into the earth itself, beneath you right now. As you lie still and comfortable, there are layers of stone and heat and ancient memory stretching down for thousands of miles. The ground beneath your home, beneath your street, beneath the oceans and the mountains and the wide open plains. It has been here for an almost unimaginable amount of time, 4.5 billion years. That number is so large that it softens into something almost dreamlike. And that is exactly where we are going tonight, into the dream of deep time. We will move slowly. There is no hurry here. We will drift together through the story of how this planet came to be, how dust and fire became oceans, how oceans became mountains, how stones slowly, patiently, beautifully became the world you are resting on right now. You don't need to remember any of this. You don't need to hold on to it. Simply let the words wash over you, the way water washes over ancient stone, softly, slowly, wearing away nothing but the tension of the day. Let your body grow heavy. Let your breathing slow. This is Sleepy Facts with Justin, and tonight, the earth itself will carry you gently to sleep. Before there was an earth, there was only quiet. A vast, dark, drifting quiet, stretching across distances so enormous that no word we have can really hold them. And floating in that quiet, spread across the deep reaches of space, was a cloud, not a cloud like the soft white ones that drift across a summer sky. This was something far older and far more still. A nebula, a slow, thin, almost ghostly collection of gas and dust, hanging in the darkness between the stars. This cloud was made mostly of hydrogen, the simplest, lightest, most ancient element in the universe. Hydrogen born in the very first moments after the Big Bang, drifting for billions of years before it found its way into this quiet corner of space. There was helium too, and small traces of heavier elements, traces of carbon, of oxygen, of iron, the remnants of ancient stars that had lived their long lives and quietly faded away. just drifted for a long, long time. It simply drifted. It had no shape, no center, no particular destination. It was just there, impossibly wide and impossibly thin, carried gently on the slow currents of the galaxy. And then something changed somewhere nearby. A massive old star reached the end of its life. In a final, brilliant moment, that star collapsed and then exploded. A supernova, a flash of light, and energy rippling outward in every direction at unimaginable speed. That shockwave traveled through the darkness and reached our quiet, drifting cloud. And the cloud began to stir. The shockwave compressed parts of the nebula, pushing the dust and gas a little closer together. And when those particles drew closer together, something ancient and inevitable took over. Gravity. The particles began pulling on each other, just barely at first, just the gentlest, most patient tugging. The way a tide pulls at the edge of the sand, softly, endlessly, without any hurry at all. But gravity is patient. Gravity never stops. And slowly, over hundreds of thousands of years, the cloud began to contract. The outer edges of the cloud began to fall inward toward the growing center of mass, and as more material gathered at the center, the pull grew stronger, which drew in more material, which made the pull stronger still. It became, as scientists beautifully describe it, a snowball effect. Not fast, not dramatic, just slow and steady and inevitable. As the cloud collapsed, something else happened. It began to spin. This is one of the most elegant things about the universe, that clouds of gas, when they fall inward under their own gravity, naturally begin to rotate. It is a consequence of something called the conservation of angular momentum, the same quiet principle that causes a spinning figure skater to turn faster when she draws her arms in close. The cloud spun faster as it shrank, and as it spun, it flattened. The way a ball of dough flattens when you spin it between your hands, the nebula gradually stretched out into a wide, thin, rotating disk, an enormous, slowly turning wheel of dust and gas, with a dense, hot, glowing knot forming at at its very center. That glowing knot at the center would eventually become our sun. The process took about 100,000 years, which sounds like a long time, and in human terms, it is almost incomprehensible. But in the language of the universe, it was barely the blink of an eye. At the heart of the collapsing cloud, pressure and heat were building to extraordinary levels. The gas was being squeezed tighter and tighter, heating up as it compressed, glowing hotter and hotter with every passing millennium. The object at the center, the proto-sun, not quite a star yet, grew dense enough and hot enough that something extraordinary began to happen. Hydrogen atoms began to fuse, 2 hydrogen atoms pressing together with enough force will combine into a helium atom, and in doing so, they release energy. Not a little energy, an almost incomprehensible amount of energy. And when enough hydrogen atoms in that central core began to fuse, the light that was released flooded outward for the very first time. The sun was born. For the first time in the history of this small corner of the galaxy, there was light, a warm, golden, steady light, radiating outward in every direction, flowing across the thin disk of dust and gas that still surrounded the young star. That disk, that flat, slowly spinning wheel of leftover material that the sun had not pulled in during its formation, would become everything else: the planets, the moons, the asteroids, and eventually the small, rocky, blue-green world where you are right now, lying still, breathing slowly, drifting toward the edge of sleep. But all of that was still to come, for now there was only the disk, slowly spinning, grains of dust moving in wide, lazy orbits around the young sun. The whole protoplanetary disk stretching out to perhaps 200 times the distance between the Earth and the sun. An area so vast it would take light itself nearly a day to cross it from edge to edge, and in the outer, cooler reaches of that disk, where the sun's heat did not reach so fiercely, something new was beginning to happen. In those cold, quiet outer regions, molecules of water began to freeze. Ice formed on the surfaces of dust grains, just the thinnest impossible coating, as delicate as a breath on a winter morning. Closer to the young sun, where temperatures were still very high, only metal and rock could condense. Only the hardest, most heat-resistant materials survived in that inner zone. The lighter gases, the methane, the water vapor, the ammonia, they were pushed outward, away from the heat, to the cold outer edges of the disk. This is why, today, the inner planets are rocky and solid, and the outer planets are great giants of gas and ice. The temperature of that ancient disk, all those billions of years ago, decided everything. But we are getting a little ahead of ourselves. For now, let the image settle softly in your mind. A wide, flat wheel of dust and gas, slowly spinning in the darkness. A young star at its center, warm and steady, and in the silence of space, grains of dust barely beginning, to drift toward one another. Gravity, patient and quiet, already beginning its next long, slow work. There is nowhere to be, nothing to do, just the quiet spinning of ancient dust, and the warmth of a new sun, and the vast, unhurried beginning of everything. Let that image hold you gently as you breathe. Slowly in, slowly out. Imagine, if you will, a single grain of dust. Not the kind of dust you might find drifting through a sunbeam in a quiet room. Though there is something lovely about that image too. This is a grain of cosmic dust, floating in the vast, rotating disk of gas and material that surrounds the young sun. It is impossibly small, smaller than the finest powder, a tiny fleck of silicate or iron, tumbling slowly through the dark, carried along on the slow current of the spinning disk. Now imagine another grain drifting nearby. They are moving at almost exactly the same speed, carried along in the same wide orbit around the young sun, and slowly, gradually, in the way that two soap bubbles floating through the air will eventually drift close enough to touch. These two tiny grains find each other. They collide, not violently, gently, a soft, slow collision at almost no relative speed. And something beautiful happens. They stick together, This is where the Earth begins. The process has a name, accretion, and it is one of the most patient, most persistent processes in the known universe. It is simply the coming together of small things into larger things, driven by nothing more dramatic than proximity and time. Dust grains clumping into pebbles, pebbles drifting together into boulders, boulders slowly accumulating into something larger still. In the early days of the solar disk, this process was governed not yet by gravity, but by something simpler: static electricity, the same quiet force that causes a balloon rubbed against a sweater to cling to a wall, or causes your hair to rise on a dry winter morning. Small particles in the disk carried tiny electrical charges, and those charges drew them gently toward one another. It happened slowly, imperceptibly slowly by any human measure. But the disk was vast, and there were countless trillions of particles, and time was the one thing the early solar system had in extraordinary abundance. Over thousands of years, the tiny clumps grew. Grains became clusters. Clusters became loose, fragile aggregates, almost like tiny snowflakes in structure, delicate and porous. These grew larger still, until they reached sizes of centimeters, then meters. At this scale, scientists give them a name: planetesimals. Small bodies of rock and metal tumbling through the disk in their wide orbits, still growing, still accumulating, still reaching out with that ancient, patient pull. And somewhere around this point, somewhere around the scale of a kilometer in size, something changed. Gravity arrived. Once a body becomes large enough, its own gravitational field becomes meaningful. It begins to actively pull material toward itself, rather than simply waiting for chance collisions. And this changes everything. Because the larger a body grows, the stronger its gravity becomes, and the more material it draws in, and the larger it grows still. Scientists call this runaway accretion, a wonderful phrase that captures something of the quiet momentum of the process. The biggest bodies grew fastest. They swept up smaller bodies in their paths, absorbing them, growing heavier, growing denser, Smaller bodies that came too close were captured and drawn in. Others collided at low speeds and merged together, like drops of water coming together on a window pane. Picture the disk during this period. It is still spinning, still orbiting the young sun. But now, scattered across that disk, are thousands of planetesimals, rocky, irregular bodies ranging from boulders to objects perhaps the size of mountains, all moving in their own orbits, all slowly, inevitably drifting toward the largest concentrations of mass, the inner solar system, where Earth would eventually form, was rich in silicate rock and iron. The temperature close to the sun had long since burned away the lighter ices and gases, leaving only the dense, hard materials behind. And from these materials, iron and magnesium and silicon and oxygen, the building blocks of our world, were slowly, patiently assembling. The collisions by this stage were no longer gentle. As planetesimals grew larger, the impacts became more energetic. A body the size of a mountain striking another body the size of a mountain at several kilometers per second releases an almost incomprehensible amount of energy. Rock melts, craters form, material is thrown outward, some of it escaping into space, some of it falling back onto the growing body. And yet, even this violent period has a kind of slow grandeur to it. These impacts happened over millions and millions of years. Not fast, not sudden, just the steady, inevitable rhythm of a world assembling itself. One collision at a time, one layer at a time, 1,000,000 years at a time, as the young Earth-to-be grew larger, perhaps to the size of Mars, perhaps larger. Something remarkable began happening in its interior. The energy released by all those impacts and the decay of radioactive elements scattered throughout the rock began generating enormous heat deep within the growing body. The interior started to melt, and when rock melts, something elegant happens. The heavier elements, the iron, the nickel, sink downward toward the center. The lighter silicate materials rise toward the surface. This process is called differentiation. and it is the reason the Earth today has an iron core at its heart. All of that heavy metal, which was once scattered evenly through the body of the young Earth, slowly sank inward over millions of years, settling into the deep, dense, brilliant core that still lies beneath you now. It is a beautiful thought. The iron in the Earth's core and the iron in your own blood, for that matter, was forged in ancient stars that died long before our sun was ever born. That iron drifted in the nebula, gathered in the disk, accumulated in the growing Earth, and then sank slowly over millions of years to the very center of the world. Ancient starlight resting at the heart of everything. Meanwhile, on the surface of the young Earth, the landscape was unlike anything we could imagine. A churning ocean of molten rock, magma, stretched across the entire surface, glowing dull red and orange in the reflected light of the young sun. Volcanoes erupted not as isolated features, but almost everywhere, constantly, releasing gases into the thin, early atmosphere. The sky above was not blue. It was something darker, something strange, a hazy, thick mixture of carbon dioxide and nitrogen, and water vapor and sulfur compounds, pressing down over the glowing surface. It was, by any measure, a hostile and extraordinary place, and yet it was ours. This roiling, violent, molten world was the earliest version of the planet you are resting on tonight. Every mountain you have ever seen, every quiet valley, every smooth river stone and still lake bed, all of it was once part of that churning surface. The violence of those early impacts is locked away, silent and still, deep in the geological record, in rocks that have been folded and compressed and worn smooth over billions of years. Accretion took about 10 to 20 million years in the inner solar system. In the grand sweep of Earth's 4.5 billion year history, that is a relatively short opening chapter, a brief, bright, chaotic beginning, and then a gradual settling, a gradual cooling, a gradual quieting. The disk was thinning. Much of the material that had once filled it had been gathered up into planets and moons and asteroids. filling the space between the planets. The wild period of constant accretion was slowly drawing to a close, and what was left in the inner solar system was a small, hot, still partially molten world, approximately the size of the Earth we know today, perhaps a little smaller, orbiting the Sun at a distance of about 93 million miles. It had no moon yet. It had no oceans yet. Its atmosphere was thin and strange, nothing like the soft air you are breathing right now. But it existed. From a cloud of drifting dust, from the patient work of gravity and time and heat, a world had been built, grain by grain, collision by quiet collision, year by endless year. Let that sit with you gently now. The ground beneath you was once drifting dust. The iron in your blood was once scattered through a cold nebula. You are, in the most literal and wonderful sense, made of ancient stars. Breathe that in slowly. Let the thought drift through you like light through deep water. You are resting on a world 4.5 billion years in the making. There is nowhere else you need to be. The scientists who study deep time have always had a gift for names. And when they looked back at the earliest chapter of Earth's long life, that first, fierce, extraordinary 500 million years of our planet's existence, they reached for a name drawn from ancient myth. They called it the Hadean Aeon, named for Hades, the Greek underworld, the realm of fire and shadow and deep, unknowable heat. It is, perhaps, the most fitting name in all of geology. The Hadean Aeon began approximately 4.5 billion years ago. At the very moment the Earth formed from the swirling disk of dust and rock we visited in our last quiet journey, and it lasted until roughly 4 billion years ago, a span of about 500 million years, a stretch of time so vast that the entire history of complex animal life on Earth could fit inside it many times over. But there were no animals then. There were no plants. There were no oceans, no gentle breezes, no soft rains falling on quiet plains. There was only fire. The surface of the early Earth was almost entirely molten, a global magma ocean, stretching from horizon to horizon in every direction, glowing with a deep, sullen heat. The rocks beneath your feet have long since cooled and hardened and been sculpted by billions of years of wind and water. But if you could somehow stand at the surface of the Hadean earth and look out across the landscape, you would see nothing but liquid rock, slowly churning, lit from below by its own immense heat. The sky above that molten surface was heavy and dark. A thick atmosphere of carbon dioxide and water vapor and sulfur compounds pressed down over the world, trapping heat, keeping the surface at temperatures far above anything we experience today. There was no oxygen in that early atmosphere, not even a trace. The air, if you could call it that, would have been entirely unbreathable. And from above, something else was falling. The early solar system, during the Hadean period, was still a crowded and dangerous neighborhood. The process of accretion had built the planets, but it had left behind vast numbers of smaller rocky bodies, asteroids, and planetesimals tumbling through the inner solar system in unstable orbits, and many of these fell to Earth. The bombardment was constant, not the occasional dramatic impact we might imagine, but a relentless rain of rocky debris, striking the young Earth's surface again and again and again, each impact releasing energy, each impact adding more heat to a surface that was already glowing. Imagine standing somewhere safe and distant, looking down at the young Earth from above. You would see a sphere of dull orange and red, wrapped in dark cloud, flickering constantly with the white flashes of impacts. It would look something like a world being slowly, patiently hammered into shape, which is, in a sense, exactly what was happening. And yet, even in this violent, fiery beginning, there were moments of quieter beauty as the interior of the earth slowly differentiated, the iron sinking to the core, the lighter rock rising toward the surface. The mantle began to develop its own slow, churning movement, heat rising from the deep interior created enormous convection currents in the mantle rock, carrying warmer material upward and cooler material downward in vast, slow loops. took millions of years to complete a single cycle. Those convection currents would, much later, drive the movement of the great tectonic plates. But in the Hadean, they were simply the deep, slow breath of a young planet, adjusting to its own internal heat. At the surface, something remarkable was beginning to happen in the later stages of the Hadean. The crust was starting, tentatively and briefly, to solidify. In places where the magma ocean had cooled a little, a thin skin of solid rock would form, dark and glassy and fragile, floating like cooling scum on the surface of a slow river. These early crustal fragments did not last long. The continued impacts shattered them. The heat below them melted them back into the magma. And yet, again and again, the crust attempted to solidify. Patience in the face of destruction is very much the theme of this early chapter of Earth's story. We know this period almost entirely from inference and theory, because the Hadean left almost no rocks behind for us to find. The violence of that era destroyed almost everything. The constant melting and remelting, the endless impacts, the churning of the mantle, all of it erased the physical record almost completely. Almost in a remote region of Western Australia called the Jack Hills, geologists have found tiny crystals of a mineral called zircon that formed approximately 4.4 billion years ago. These are the oldest known materials on Earth. Small, almost impossibly ancient fragments that somehow survived the violence of the Hadean, preserved within younger rocks like tiny time capsules, sealed at the very dawn of the world. Those zircon crystals are smaller than a grain of sand, and yet they carry within their crystalline structure a memory of temperatures and pressures from the earliest days of the Earth's crust, a memory scientists can read today using the decay patterns of radioactive elements locked within the crystal. The zircons whisper in their quiet mineral language of a world slowly cooling, of water, perhaps, already beginning to condense, of the first impossible hints of a surface. There is a kind of wonder in that, the oldest thing on Earth, The oldest thing you will ever encounter in any form is smaller than a grain of sand, resting in a museum drawer somewhere, 4.5 billion years old, still holding its ancient secrets toward the later part of the Hadean, roughly 4.1 to 3.8 billion years ago. The bombardment intensified dramatically in what geologists call the late heavy bombardment, something perhaps a shift in the gravitational influence of Jupiter or Saturn destabilized a vast reservoir of asteroids and sent them raining inward across the solar system, the moon's surface, with its ancient craters still preserved for us to see on clear nights, is our best record of this period. Every crater you can see on the moon with a pair of binoculars on a quiet evening was carved during this ancient storm of impacts. The Earth received the same bombardment, but our planet's restless geology has long since erased most of the scars. The moon, quieter and geologically still, kept the record for us. Every time you glance up at the moon on a still night, you are looking at the preserved face of the Hadean bombardment, a quiet memorial to the most violent chapter in our planet's early life. And yet, even during the late heavy bombardment, the Earth was changing, cooling slowly in the spaces between impacts. The magma ocean was gradually, over millions of years, developing a more permanent crust. Water, delivered partly by the impacts of icy comets and asteroids, was beginning to accumulate. Temperatures, while still extreme, were slowly falling from the impossible heights of the earliest Hadean. The world was edging, almost imperceptibly, toward something more habitable. Not quickly, never quickly. The Earth does nothing quickly, but with the patience of deep time, the surface cooled, the crust thickened, the bombardment slowly, gradually, over many millions of years, began to ease. By the very end of the Hadean Eon, the Earth was still an extraordinary, alien-looking place, mostly rock, still geologically violent, with a sky bearing no resemblance to the blue canopy you know, but it was no longer entirely molten. There were solid surfaces. There were, perhaps, the very earliest pools of liquid water forming in low-lying areas where the surface had cooled enough to allow it, and somewhere in those earliest tentative pools, somewhere in the quiet spaces between the rocks, where chemistry was doing its own slow, patient work, the first stirrings of something even more remarkable were beginning. But that is a story for another section. For now, let the image of the cooling, ancient earth settle gently in your mind. A world of dark rock and quiet heat. A world still finding its shape. A world that had no idea, in all its fiery youth, what it would one day become. Let your breathing slow. Let your body settle deeper. The ancient world is cooling around you, stone by patient stone, and you are already drifting slowly toward the edge of sleep. Of all the stories written into the rock and light of our solar system, this one may be the most astonishing. It is the story of how the Earth, already young and still cooling from its fiery Hadean infancy, was struck by another world, not a small asteroid, not a drifting fragment of rock. Another world, a body roughly the size of Mars, perhaps half the diameter of the early Earth, traveling on a long, slow orbital path that had, over millions of years, been drawing gradually, inevitably closer. Scientists call this ancient body Theia, named for the Greek Titan goddess, who, in mythology, was the mother of the moon. It is a beautiful name for a world we will never see, a world that no longer exists, because Theia and the early Earth collided approximately 4.5 billion years ago in the most consequential impact in the history of our planet. And from that collision, the moon was born. The story of how we came to understand this begins not on Earth, but with the rocks brought back from the moon by the Apollo astronauts in the late 1960s and early 1970s, when scientists analyzed those lunar rocks carefully. They noticed something extraordinary. The composition of moon rock, its ratio of minerals, its isotopic signatures, the precise chemical fingerprint of its material, was almost identical to the composition of Earth's mantle rock. This was deeply puzzling for a long time. If the moon had formed elsewhere in the solar system and been captured by Earth's gravity, you would expect its chemistry to be quite different from Earth's. If it had condensed from the same disk of material as the Earth in the same region of space, the similarity might make some sense. But the degree of similarity was striking enough to suggest something more intimate, something that spoke of a deep, shared origin. The giant impact hypothesis, as it came to be called, slowly emerged as the most convincing explanation. And what it describes is almost dreamlike in its scale. Theia, in the models scientists have developed, formed in the same region of the inner solar system as the Earth. For millions of years, it orbited the Sun on a path close to Earth's own, growing in size through accretion, just as the Earth had. The two bodies occupied what astronomers call a gravitationally balanced position, a stable zone where Theia could orbit for a very long time without immediately colliding with its neighbor. But gravitational stability in the early solar system was always temporary. The subtle gravitational nudges of Jupiter and the other giant planets slowly, invisibly disturbed Theia's orbit over millions of years. Its path shifted, and once it shifted, the outcome was eventually inevitable. The collision, when it finally came, was not a direct head-on impact. It was an oblique strike, a glancing blow angled gently, the way one billiard ball might strike another at the edge rather than the center. This angle was, in a very real sense, what made the moon possible. A direct head-on collision might have shattered both bodies entirely, or merged them violently into a single, drastically altered world. Instead, the oblique impact did something far more interesting. Theia plunged partially into the Earth, its iron core sinking and merging with the Earth's own iron core, adding to it, deepening it. But the enormous energy of the impact, an energy so vast it is almost impossible to express in human terms, vaporized and ejected an enormous quantity of material from both bodies outward into space. For a brief, extraordinary moment, the Earth was surrounded by a vast ring of vaporized rock. a glowing disk of superheated silicate vapor and molten droplets orbiting the Earth at tremendous speed, spreading out in a wide, hot cloud that caught the young sun's light and scattered it in all directions. Picture it for a moment. The Earth glowing from within from the heat of the impact, wrapped in a brilliant ring of vaporized rock. The sky above the surface, an unrecognizable hellscape of heat and light. The impact had been so energetic that it had remelted the Earth's entire surface, resetting the long, slow work of cooling that the Hadean crust had just barely begun. But from that violence, something gentle was already beginning to form. The debris in the ring around the Earth began to cool. The vaporized rock condensed into droplets of molten material. Those droplets cooled further into solid fragments, and those fragments, just as the planets had formed from the original solar disk, began to clump together under their own gravity. Within perhaps just a few thousand years, an eye blink in geological time, enough of the debris had aggregated into a single body to form a recognizable moon. It was rough and irregular and covered in a deep ocean of molten rock. It was much closer to the Earth than it is today, perhaps 15 times closer, looming enormous in the sky above the still glowing surface of its parent world. And it was beautiful in its own fierce and alien way. The newly formed moon and Earth were tidally locked in an intimate gravitational embrace. The moon's gravity raised enormous tides in the Earth's magma ocean, slowly, steadily pulling at the molten surface. The Earth's gravity, in return, was gradually slowing the moon's rotation, working on it with the same patient, irresistible pull that the tides work on stone. Over millions of years, that gravitational interaction began doing something still happening today. The moon has been slowly moving away from the Earth. In those earliest days after the impact, the moon was so close that it would have filled a significant portion of the sky. Today, it is a calm, familiar silver disk, small enough to cover with your thumb at arm's length. The distance between the Earth and moon increases by about 3.8 centimeters every year. The rate at which your fingernails grow. Slowly, patiently, year by year, the moon's influence on the earth has been profound in ways we are still understanding. Its gravitational pull stabilizes the tilt of the Earth's axis, keeping our planet from wobbling erratically on its rotational path. Without the moon, the Earth's axial tilt might vary dramatically and chaotically over millions of years, producing climate swings so extreme that the development of complex life might never have been possible. The moon, in a very quiet and understated way, may be one of the reasons that life, as we know it exists at all. And there is one more thing worth resting with for a moment: the material that makes up the moon. That beautiful, silver, softly glowing presence you see on clear nights came largely from the mantle of the early Earth. The moon is, in a deep and literal sense, a part of our own world, a piece of Earth flung into the sky by an ancient collision, slowly circling home. Every time you look up at the moon on a quiet evening and feel some ancient, wordless sense of connection to it, you are not imagining things. That connection is real. It is geological. It is 4.5 billion years old. The moon is family. And now, as you rest here in the quiet, the same moon that formed in fire and catastrophe all those billions of years ago is perhaps casting its soft silver light through a window nearby. It is still there, still slowly drifting away, centimeter by centimeter, year by year, still stabilizing the tilt of the world you sleep on, still raising tides on every ocean shore. The violence that created it is long, long gone. What remains is only the gentle light. Let that soft light move through your thoughts now, like moonlight through still water. Let it carry the last of the day's weight gently away. You are held by the earth, watched over by the moon. Everything is ancient. Everything is still. Everything is well. Breathe slowly. Drift. After the fire, there was cooling. Not sudden, not swift. Nothing in the deep story of this earth has ever been sudden or swift. slowly over millions of years, the surface of our world remelted and rescorched by the great collision that gave us our moon began once again to lose its heat to the cold emptiness of space. This is one of the quietest, most patient processes in all of geology. Heat simply radiating outward from a surface into the dark. The way a stone warmed by the afternoon sun slowly releases its warmth into the cool of the evening, except that this was a world-sized stone, and the evening lasted millions of years. The magma ocean at the surface began, in places, to develop a skin. Just as you might see a thin, wrinkled skin forming on the surface of heated milk as it cools in a pan, the surface of the young earth began to develop a fragile, dark crust of solidified rock, basalt, mostly a dense, fine-grained volcanic rock, dark as a winter sky, cooling and hardening wherever the surface temperature dropped just low enough to allow it. The crust was thin. It was fragile. It broke apart and was swallowed back into the magma in many places, remelted and recycled endlessly in those first hundreds of millions of years. But it kept forming again and again with the same quiet persistence that defines everything about this planet's story. The crust reached upward toward solidity, and above that cooling crust, something was happening in the sky. The early Earth's atmosphere was dense and heavy. A thick blanket of carbon dioxide, nitrogen, water vapor, and gases exhaled by the constant volcanic activity below. This atmosphere was nothing like the clear, oxygen-rich air we breathe today. It was hot and strange and pressing, but it contained something of extraordinary importance. Water vapor had been part of the earth since its formation, locked in the minerals of the rocky bodies that had accreted together to build the planet, and delivered in additional quantities by the impacts of icy comets and asteroids during the long Hadean bombardment. All of that water in those early volcanic and impact-heated conditions had existed only as vapor, suspended in the thick atmosphere above the molten surface. But as the surface cooled And as the atmosphere itself began to lose some of its extreme heat, a threshold was slowly, inevitably approaching, a temperature at which water vapor could no longer remain a gas, the point at which it would begin to condense, the dew point of an entire world. And then, one day, if we can call any moment in geological time a day, it happened. A droplet of water formed in the high atmosphere of the early Earth. Just one droplet, perhaps, or perhaps countless droplets across the sky simultaneously. We cannot know the precise moment, and there is something beautiful in that uncertainty, but somewhere in that dense, hot sky, a droplet of liquid water formed, and it fell. The first rain. That first rain would not have looked like any rain you have seen. The droplets falling from the high atmosphere toward the still partially molten surface would have been falling through air far hotter than any storm you have ever experienced. Many of those first droplets would have evaporated again long before they reached the ground, flashing back into vapor as they passed through the hot, lower atmosphere. But the surface was cooling, and as it cooled further, the rain began to reach it. When those first drops of water landed on the hot, volcanic surface of the early Earth, they boiled instantly and explosively back into steam. The same sizzling flash you might hear if you dropped a single droplet of water onto a very hot pan. The surface hissed and steamed. The water returned to the atmosphere, and then it cooled and condensed again, and fell again. This cycle, rain falling, evaporating, condensing, falling again, continued for an extraordinarily long time. It was a planetary scale distillation process. Water endlessly cycling between surface and sky. Each cycle transferring a little more heat away from the surface and into the atmosphere. Each cycle allowing the surface to cool just a fraction further, and slowly, the surface cooled enough that the rain began to stay. Water pooled in low-lying areas, at first just shallow puddles, warm and still, resting in depressions in the cooling volcanic rock, then wider accumulations, deepening as more rain fell. And as volcanic rock continued to release water it had held trapped, in its mineral structure for millions of years. The water was not clear and blue as we might imagine. It was likely warm and slightly acidic, tinged with dissolved minerals from the volcanic rock, under a sky still thick with carbon dioxide and volcanic gases. But it was water, liquid water, resting on the surface of the earth. And over millions of years, those first shallow pools deepened and expanded. Basins filled, low regions flooded, water poured from higher ground into lower ground, just as it does today, following gravity with that same quiet obedience it has always shown. The young oceans began to form by roughly 4 billion years ago, toward the very end of the Hadean Eon, or the beginning of the next great chapter of Earth's story. The surface of the earth was covered, at least in part, by ocean, a warm, shallow, mineral-rich global sea. Much of it perhaps only a few hundred meters deep, broken here and there by the dark peaks of volcanic islands rising above the surface. No continents yet, not as we know them. The crust was still thin and uniform, dark basaltic rock, nothing like the thick, buoyant granite masses that would eventually become the great continental landmasses. But there was an ocean, there was a surface, there was the sound, if anyone had been there to hear it, of waves. Think about what that means. The soft, rhythmic sound of waves on a shore. That sound so ancient in our memory, so deeply calming to so many of us, has been playing somewhere on this planet for nearly 4 billion years without stopping, generation upon generation upon generation, wave after wave, shore after shore, across every age and every era of Earth's history. That sound was already old before the first living cell existed. It was already ancient before the first fish swam, before the first tree grew, before the first footprint was pressed into coastal mud. The waves have simply never stopped. The cooling of the earth and the arrival of the oceans did something else of enormous importance. It began removing carbon dioxide from the atmosphere. When water falls as rain, it absorbs carbon dioxide from the air, forming a weak carbonic acid. That acidic rainwater falls on rock, slowly dissolving it, carrying dissolved minerals, including carbon, into rivers and eventually into the sea. In the ocean, those dissolved minerals combine and settle to the seafloor, locking the carbon away in layers of sediment. This process, called the carbon silicate cycle, has been quietly regulating the Earth's temperature for billions of years. A slow, self-correcting thermostat built into the chemistry of rock and rain. When the planet warms, rainfall increases. More carbon dioxide is drawn from the atmosphere, and the planet cools. When it cools too much, less rain falls, less carbon dioxide is removed. Volcanic activity replenishes what is lost, and the planet warms again. A breath, a slow planetary breath, in and out over millions of years, keeping the world within the narrow band of temperatures where liquid water can exist, where life can exist, where you can exist. It is a staggering thing to contemplate that the comfortable, temperate world you live in, the blue skies and mild seasons and gentle rains, are the product of a chemical feedback loop 4 billion years old, built into the very rock and ocean and air of this world, running silently and continuously beneath the surface of every ordinary day. The first rain did more than fill the oceans. It set in motion a process that has protected and sustained life for all of the time that life has existed. So let the rain, if you hear it tonight, or let the memory of rain, soft and steady on a quiet roof, carry something extra with it now. Let it be a reminder of that first ancient downpour, those first warm drops sizzling on hot volcanic rock, the beginning of something that has never since stopped. Let it carry you downward softly, the way water finds its way through stone, deeper into the quiet, deeper into rest. Beneath you right now, there is an entire other world, not a metaphor, not a poetic notion, a literal, physical world of extraordinary complexity and beauty, layered like the rings of an ancient tree, stretching downward from the soil under your home, all the way to the very center of the earth, a distance of about 6,371 kilometers, you will never see most of it. No human being ever has, or likely ever will. The deepest hole ever drilled into the earth, the Kola Super Deep Borehole in northwestern Russia, a project that took the Soviet Union nearly 20 years of continuous drilling, reached only about 12 kilometers deep before the heat and pressure made it impossible to go further. 12 kilometers, less than 0.2% of the way to the center. The earth keeps its deepest secrets very well, and yet we know what is down there. We know it not from drilling, but from listening, from the patient, careful study of seismic waves, the ripples of energy that travel through the earth when an earthquake occurs, bending and bouncing and slowing as they pass through materials of different densities. Scientists have spent over a century reading those waves the way a doctor reads an X-ray, building up a picture of the Earth's interior that is, in its own way, just as detailed and just as beautiful as anything visible on the surface. What those waves have revealed is a world of distinct layers, each one different in composition and temperature and behavior, each one playing its own quiet and essential role in making the surface of this planet the place it is. Let us travel downward together, slowly, gently. We begin at the surface where you are now. The outermost layer of the earth is called the crust. It is the thinnest layer by far, the delicate, cooled outer skin of a world that is still, at its heart, extraordinarily hot. Under the continents, the crust is typically between 30 and 50 kilometers thick. Roughly, the distance you might drive in half an hour on an open highway. Under the oceans, it is thinner still, sometimes only 5 to 10 kilometers from the seafloor to the boundary with the layer below. The continental crust is made largely of granite and similar rocks, lighter in color, lower in density than the dark basalt of the ocean floors. This difference in density is deeply important. It is why the continents float higher on the underlying mantle than the ocean floors do. The way a thick plank of pine floats higher in water than a thin plank of oak, the light lightness of granite is what keeps the continents elevated, what gives the world its mountains and high plains and dry land. Without it, the entire surface of the earth might lie beneath a uniform global ocean. The crust is where all of human history has taken place. Every city ever built, every road ever laid, every seed ever planted in soil, all of it resting on this thin, cool, fragile outer layer. It is easy, living on the surface, to think of the earth as solid and permanent and deep. But the crust is, in geological terms, barely a coating, a thin shell on an enormous, living, heat-filled world. Beneath the crust lies the boundary that geologists call the Mohorovičić discontinuity, named for the Croatian scientist Andrija Mohorovičić, who discovered it in 1909 by studying the way seismic waves changed speed at a certain depth. Scientists, with some affection, shorten it to simply the Moho. It is the line where the cooled, rigid crust gives way to something different, something slower and hotter and more alive. The mantle is by far the largest layer of the earth, extending from the base of the crust down to a depth of about 2,900 kilometers. It makes up approximately 84% of the Earth's total volume. If you could somehow hollow out the Earth and look at the mantle alone, it would be an enormous thing. A thick, dark, slowly moving shell of rock, hotter than you can easily imagine, behaving in ways that challenge ordinary intuition because the mantle is solid, and yet it flows. This is one of the most beautiful and counterintuitive things about the Earth's interior. The rock of the mantle, under the enormous pressures and temperatures found at those depths, temperatures ranging from around 1,000 degrees Celsius near the top to perhaps 3,500 degrees near the bottom, behaves not like the rigid stone you might pick up from a riverbed, but like an extraordinarily thick, slow fluid. Given enough time, it creeps and flows and convects, carrying heat from the deep interior upward toward the surface in vast, slow currents. How slow? A typical mantle convection current moves at a rate of perhaps a few centimeters per year, roughly the same rate at which your fingernails grow, the same rate at which the moon is drifting away from the earth. The earth is full of these quiet, unhurried rhythms. It is those slow convection currents in the mantle that drive the movement of the great tectonic plates at the surface, pushing them apart in some places, drawing them together in others, carrying continents on their backs across the face of the world over hundreds of millions of years. The mantle is the engine beneath everything, silent and invisible and slow, but responsible for every mountain range, every ocean trench, every volcanic island that has ever risen from the sea. Deep in the lower mantle, the pressure becomes so extreme that the rock there takes on different properties. Denser crystal structures, different mineral forms that exist nowhere on the surface and can only be created under the crushing weight of hundreds of kilometers of rock pressing down from above. Some of these high-pressure minerals have only been identified in the last few decades. Their existence inferred from laboratory experiments that compress tiny rock samples to simulate the conditions deep in the earth. The earth, even now, is still teaching us things about itself. And then, at a depth of about 2,900 kilometers, the mantle ends. The temperature rises sharply. The density changes abruptly and dramatically. Seismic waves that pass through the mantle bend sharply at this boundary, some of them reflecting back entirely. This is the core mantle boundary, one of the sharpest and most dramatic transitions in the interior of our planet, and below it lies the outer core. The outer core is liquid, a vast ocean of molten iron and nickel, about 2,260 kilometers thick, circling the inner core in slow, swirling currents driven by the heat rising from below and the rotation of the earth above. Temperatures here range from about 4,000 to 5,000 degrees Celsius, hotter than the surface of the sun. Those slow, swirling currents of liquid iron are doing something of enormous importance. They are generating the Earth's magnetic field. The movement Earth's rotation creates a dynamo effect, a self-sustaining magnetic field that extends far out into space around the Earth. Invisible but vital, it is this magnetic field that deflects the solar wind. The constant stream of charged particles flowing outward from the sun, away from the Earth's surface. Without it, the solar wind would slowly strip away the atmosphere over millions of years, the way it has stripped away the thin atmosphere of Mars. The magnetic field is the Earth's invisible shield, and it is powered by nothing more than the slow, quiet swirling of liquid iron in the dark. And at the very center of all of this, at the absolute heart of the world, at a depth of 6,300 kilometers beneath the surface where you are lying now, is the inner core, a solid sphere of iron and nickel, approximately 1,200 kilometers in radius, roughly the size of the moon. Under pressures so unimaginably vast that iron, which would be molten at these temperatures in any other context, is forced into a solid crystalline state. The inner core is the most compressed, the most isolated, the most ancient and undisturbed part of our planet. It has been there, slowly growing as the Earth cools over billions of years, accumulating atom by atom at the boundary, where liquid outer core gradually solidifies. It grows by approximately 1 millimeter every year, patient and quiet and entirely in the dark. Think about that for a moment as you lie here in your own quiet at the center of the world. Iron crystals are slowly, silently forming. The heart of the Earth is growing imperceptibly in the deep. Everything is moving, even in the stillness. Everything is growing, even in the dark. Let the layers settle through your thoughts like sediment through still water. Crust, mantle, outer core, inner core, each one resting inside the next, like the layers of a dream within a dream. You are lying on the outermost of those layers, the thin, cool, quiet surface of an ancient, living world. Let yourself rest there, completely still, completely held. There is a word that geologists use for the ancient, stable cores of the continents: cratons, from the Greek word for strength. These are the oldest surviving pieces of continental crust on Earth. Vast, quiet platforms of rock that have endured for billions of years, while everything around them has been folded, melted, subducted, and remade. They are the foundation stones of the world, and they formed during the long, extraordinary chapter of Earth's story we are visiting now, the Archean Eon. It began approximately 4 billion years ago as the worst of the Hadean bombardment finally eased, and the surface of the Earth settled into something a little more permanent, and it lasted until about 2.5 billion years ago, a span of 1.5 billion years, the longest of any of Earth's great eons, a stretch of time so immense it makes the mind grow soft and still just trying to hold it. The world at the beginning of the Archean looked almost nothing like the world we know. There were no continents as we would recognize them, just scattered volcanic islands rising from a warm, shallow, global ocean, dark rock jutting above the waterline, surrounded on all sides by the calm gray-green sea. The sky was not blue. It was likely a pale orange haze, thick with methane and carbon dioxide, filtering the light of a sun that burned somewhat less brightly than it does today. It was warmer than you might expect, given that fainter sun. The greenhouse effect of that thick early atmosphere kept the surface temperatures comfortably above freezing. Another of the Earth's quiet, self-regulating balances. Compensation built into the chemistry of the air. The world was warm and still and strange. And it was, for the first time in its history, building something that would last. The crust during the Archean was thickening and stabilizing. The dark basaltic ocean floor rock was being subducted, drawn down into the mantle at the edges of where crustal plates met. And in the deep heat of the mantle, it was being transformed and reprocessed. The lighter granitic material from that reprocessing rose back toward the surface, accumulating into thicker, more buoyant masses. The first true continental crust was slowly assembling itself, rising a little higher from the ocean with each passing million years, we can still touch pieces of that ancient crust today. In the Northwest Territories of Canada, there is a formation of rock called the Acasta gneiss. It is approximately 4 billion and 3 million years old, making it the oldest known intact piece of rock on the surface of the Earth. It is a beautiful banded rock, dark and light layers folded together in slow curves, the product of enormous heat and pressure applied over immense time. If you held a piece of it in your hand, you would be holding something that solidified when the Earth was less than 600 million years old, before any life had left a fossil record, before any ocean floor had been recycled completely, before almost everything we think of as the story of this planet had yet begun. In Western Australia, the ancient Pilbara Craton preserves rocks nearly as old, great expanses of some of the most ancient continental crust on Earth, gray and worn and quiet under the wide Australian sky. And in Greenland, the Isua Greenstone Belt holds rocks dating back 3.7 to 3.8 billion years, including what may be some of the oldest sedimentary formations ever found, rocks that were once seafloor sediments, now metamorphosed and tilted by billions of years of geological movement, but still whispering of the ancient ocean that once lay above them. These old rocks are among the most precious things on Earth. Not precious in the way of gems or metals, though they have their own austere beauty. Precious because they are memories, the only physical memories we have of a world that no living thing witnessed. But the Archean was not lifeless. This is the most extraordinary thing about this ancient eon. Somewhere in the warm, mineral-rich waters of the Archean Ocean, life appeared, quietly, without fanfare, without any witness except the slow, patient chemistry of the sea. We do not know exactly when. We do not know exactly where. We do not know the precise sequence of chemical steps that led, in the warm dark of an ancient ocean, from complex organic molecules to the first thing that could truly be called alive. This is one of the great open questions of science. a question that researchers are still working on today and may not fully answer for generations. But we know it happened because the evidence is written in rock in the Pilbara region of Western Australia. In rocks approximately 3.5 billion years old, there are structures called stromatolites. Layered, dome-shaped formations of sediment built up slowly over long periods of time by communities of microscopic living organisms, specifically cyanobacteria, single-celled life forms capable of using sunlight to drive chemical reactions. Each thin layer in a stromatolite represents a season, or perhaps a year, of microbial growth. Each layer is a page in the oldest biological record on Earth. Stromatolites are not dramatic-looking things. If you saw one without knowing what it was, you might take it for an ordinary rounded rock, worn smooth by water. Knee-high, perhaps, or smaller. A gentle dome of gray-brown stone, resting quietly by the edge of the water. Nothing to suggest, at first glance, that you were looking at the work of the oldest living communities our planet has ever produced. But those quiet domes are among the most profound objects in existence. They are proof that life found a way. In a world with no oxygen in the air, no ozone layer to shield the surface from ultraviolet radiation, no complex chemistry, no shelter in that difficult early world, something tiny and determined began to grow, and it has not stopped growing since. Living stromatolites still exist today in a shallow, hypersaline lagoon called Hamelin Pool in Shark Bay, Western Australia. They grow in those shallow, salty waters much as their ancestors grew in the Archean Ocean, building their slow layers of sediment, generation upon generation. They are the closest thing we have to a living window into the deepest past. A direct, breathing, growing connection to the world of 3.5 billion years ago. They are unhurried and unremarkable to look at, and they are among the most extraordinary things alive. The Archean Ocean, during this long eon, was teeming with microbial life long before anything more complex appeared. Single-celled organisms without nuclei, prokaryotes, populated the warm, shallow seas, living in mats and films and clusters on the seafloor, extracting energy from sunlight and from chemical reactions in the water. They were simple by any measure, but they were alive, and they were, in ways we are still discovering, already beginning to change the world around them. The cyanobacteria, in particular, were doing something revolutionary. They were producing oxygen as a byproduct of photosynthesis. Tiny, invisible quantities at first, far too little to accumulate in the atmosphere, immediately absorbed by dissolved iron in the ocean water, but they were producing it. Year after year, generation after generation, that slow oxygen production was continuing. The stage was being set very quietly for a transformation that would not arrive until the following eon, but whose origins lay here in the Archean Sea. Life was already reshaping the chemistry of the world. It had barely arrived, and it was already leaving its mark. Toward the end of the Archean, the first recognizable continents were beginning to assemble. Small cratons had formed and were slowly drifting toward one another, pushed by the mantle currents below. The ocean was still vast. Land was still a minor feature of the planetary surface. But there was land, rocky, barren, without a trace of soil or plant, or even the faintest green, just bare volcanic rock, dark under the orange sky, surrounded by the warm, life-filled sea. No wind carried seeds, no rain carved valleys into soil, no roots split stone. The land was entirely naked rock, slowly being weathered by rain and temperature into the first thin layers of sediment. Patient chemistry doing its patient work, breaking rock into ever smaller fragments, fragment by fragment, millennium by millennium. Everything was moving towards something, slowly, without knowing it, without any intention at all. Just the quiet unfolding of chemistry and physics and time, building one layer on top of another, one era dissolving into the next. The Archean is a chapter of deep quiet, of things beginning so slowly they are barely distinguishable from stillness. A bacterium here, a stromatolite there, cratons slowly thickening, a continent barely beginning to form. And yet from that deep quiet, everything came. Every living thing on earth today traces its lineage back to those first Archean microbes. Every rock on every mountain descends from those first ancient crusts. Every ocean, every river, every raindrop carries the memory of that first warm Archean sea. It all began in the quiet, just as sleep does. Let yourself follow it there now, into the deep, still, patient dark where everything begins. The ground beneath your feet feels solid, permanent, utterly still. And in the span of a human lifetime, it very nearly is. The street outside your window has not moved in any way you would notice. The mountains visible from your nearest high place have looked the same for every generation of people who have ever lived in their shadow. The shape of the coastline on a map you studied as a child is the same shape it holds today, but stretch that window of time outward, further than a lifetime, further than a civilization, further than the entire span of human existence. And the ground begins to move, slowly, silently, with absolute patience and absolute certainty. The great plates of the earth's crust are drifting right now beneath you. They have been drifting for billions of years. And in the vast, unhurried timescale of geology, they have carried whole continents from one side of the world to the other, opened oceans where there was once dry land, and raised mountains where there was once open sea. This is the theory of plate tectonics, and it is one of the most beautiful, most unifying ideas in all of science. The Earth's crust and the rigid uppermost layer of the mantle together form a shell called the lithosphere. This shell is not one continuous piece. It is broken into a mosaic of large and small fragments. The tectonic plates, roughly 15 major ones, and a scattering of smaller ones, fitting together at their edges like the cracked shell of a hard-boiled egg. Each plate is typically between 60 and 200 kilometers thick, and each one is in slow, constant motion, carried on the back of the convecting mantle below. The largest of these plates is the Pacific Plate, covering much of the floor of the Pacific Ocean. The Eurasian plate carries Europe and Asia. The African plate, the North American plate, the South American plate, the Antarctic plate, the Indo-Australian plate, each one a vast slab of rock, moving in its own direction at its own pace, following the slow currents of the mantle beneath it as faithfully as a leaf follows the current of a quiet stream. The speeds are extraordinary in their gentleness. Most plates move at between 1 and 10 centimeters per year. At the slower end, this is about the rate at which your hair grows. At the faster end, about the rate at which your fingernails grow. The fastest moving plate we know of, the Tonga plate in the Southwest Pacific, moves at up to 24 centimeters per year, which still amounts to less than the length of your hand in 12 months. And yet, given enough time, even the slowest drift reshapes everything. The idea that continents might move was first proposed seriously by a German scientist named Alfred Wegener in 1912. He noticed, as others had before him, that the eastern coastline of South America and the western coastline of Africa fit together with remarkable precision, like two puzzle pieces that had been separated. He also noticed that the same fossils appeared on both continents, in the same rock layers, even though thousands of miles of ocean now separated them. And he found that identical mountain chains, interrupted today by the Atlantic Ocean, lined up perfectly when you pushed the continents back together on a map. Wegener called his idea continental drift. He proposed that all the continents had once been joined in a single vast landmass, which he called Pangaea, from the Greek for all lands. And he was right, but for decades, the scientific community resisted his idea, largely because he could not explain the mechanism. How could something as massive as a continent possibly move through solid ocean crust? The answer came gradually. Through the middle decades of the 20th century, as oceanographers began mapping the ocean floor in unprecedented detail, what they found there was astonishing. Running down the center of the Atlantic Ocean, they discovered an enormous underwater mountain range, the Mid-Atlantic Ridge, stretching from the Arctic to the Antarctic, the longest mountain range on Earth, almost entirely hidden beneath the sea. And along the crest of that ridge, they found something even more remarkable. The ocean floor was spreading. New rock was being created continuously at the ridge, welling up from the mantle below as molten basalt, cooling and hardening, and then being pushed slowly outward to either side as new material rose behind it. The Atlantic Ocean floor is, right now, growing wider by about 2.5 centimeters every year, pushing Europe and North America gently apart. The ocean floor is a conveyor belt, slowly carrying the continents on its back at the edges of the plates where they meet and interact. The geology becomes dramatic and varied. Where two plates pull apart, as at the Mid-Atlantic Ridge, magma wells up and new crust forms. A process so continuous and reliable that the seafloor rock closest to the ridge is always the youngest, and the rock furthest from the ridge is always the oldest. The ocean floor is a record, written in magnetic stripes, of millions of years of spreading, a barcode of geological history pressed into the basalt of the deep ocean. Where two plates push together, things become more complicated. If an oceanic plate meets a continental plate, the denser oceanic crust slides beneath the lighter continental crust in a process called subduction. The oceanic plate dives downward into the mantle, returning to the deep interior the material that once welled up at a distant ridge. At these subduction zones, the descending plate carries water and minerals down into the hot mantle, triggering volcanic activity above. The great volcanic chains of the Pacific, the Cascades in North America, the Andes in South America, the volcanoes of Japan and the Philippines, all sit above subduction zones, fueled by the slow descent of oceanic plates into the deep. Where two continental plates collide, neither will subduct easily. Continental crust is too light, too buoyant to dive into the mantle. Instead, when continents collide, the crust crumples, it folds and thickens, pushing upward into mountain ranges of extraordinary height. Himalayas, the highest mountains on Earth, home to Everest and dozens of other peaks above 8,000 meters, are the product of the Indian subcontinent colliding with the Eurasian plate, a collision that began about 50 million years ago and is still ongoing. The Himalayas are still rising today by several millimeters each year, still pushed upward by the slow, irresistible pressure of two continents pressing together. Mountains are not permanent fixtures of the landscape. They are moments in a process. They rise, and then they are worn down by rain and ice and wind over millions of years. Their material carried by rivers to the sea, deposited on ocean floors, eventually subducted or accreted back into new continental crust, the material of an ancient mountain range might, hundreds of millions of years later, find itself part of a new mountain range on the other side of the world. Stone travels. It just takes a very long time, and through all of this movement, through all the collisions and separations and rifts and ridges, the face of the earth has been continuously, slowly redrawn. 300 million years ago, the supercontinent Pangaea was still whole, one enormous landmass surrounded by a single global ocean called Panthalassa. Before Pangaea, there were other supercontinents, Rodinia, assembled nearly 1 billion years ago, and older still, Nuna and Kenorland, assembled in the depths of the Proterozoic. The continents have come together and drifted apart in a slow, repeating cycle that geologists call the supercontinent cycle, operating on a rhythm of roughly 500 million years. Together, then apart. Apart, then together. An endlessly patient waltz performed on the surface of a living planet. And the dance is not finished. The Atlantic Ocean, currently widening, will not widen forever. In perhaps 200 million years, models suggest the Atlantic may begin to close again as new subduction zones form along its edges. The continents will drift toward new configurations we cannot fully predict. New mountain ranges will rise. New oceans will open where there is today dry land, the world you know. This particular arrangement of continents and oceans and mountain ranges that seems so fixed and permanent on any map is just one frame in a very long, very slow film. The film has been running for 4 billion years, and it is nowhere near its end. But right now, in this moment, everything is still. The plates are moving, yes, but so slowly that stillness is the only word that fits the present moment. The mountains outside are exactly where they were this morning. The ocean is exactly where it was when you woke. The ground beneath you is solid and quiet and held. Rest in that solidity now. Feel the deep, ancient patience of the rock beneath you, rock that has drifted across oceans, been raised into mountains, worn down into plains, and come to rest at last, exactly here, carrying you, holding you still. There is a sound that people who live near volcanoes sometimes describe. Not the roar of an eruption, not the crack of splitting rock. Something quieter than that. A low, deep, almost subsonic rumble, felt more in the chest than heard with the ears, a vibration that seems to come from everywhere and nowhere at once, rising from somewhere far below the ground, passing through stone and soil before reaching the surface. The breath of the deep earth, working its way upward through miles of rock. Volcanoes are, in the most literal and beautiful sense, windows into the interior of our world. They are places where the heat and material of the deep mantle break through the surface, carrying with them gases and minerals and energy from depths we could never otherwise reach. They are ancient beyond measure, present on every continent, scattered across every ocean floor. And they have been among the most quietly important forces in shaping the world we know. We tend, understandably, to think of volcanoes in terms of their most dramatic moments. The explosive eruption, the ash cloud rising into the stratosphere, the rivers of glowing lava moving slowly downhill in the dark. These are extraordinary things to witness, and the geological record is full of eruptions that genuinely reshaped landscapes and altered climates. But most volcanoes, most of the time, are not erupting. They are simply present, warm and still and patient, holding their heat deep inside, breathing slowly through hot springs and fumaroles, and the faint smell of sulfur on a quiet morning. And even the eruptions in the vast timescale of geology are not disasters, they are renewal. Volcanoes form in several ways, each one connected to the great movement of the tectonic plates we explored in our last section. The most common type of volcano forms above subduction zones, where an oceanic plate descends beneath a continental plate and carries water and minerals down into the hot mantle. That water lowers the melting point of the surrounding rock, causing it to melt and form magma. The magma, lighter than the solid rock around it, rises slowly through the crust, finding cracks and weaknesses until it reaches the surface and erupts. These are the volcanoes of the Pacific Ring of Fire, the great chain of volcanic peaks that encircles the Pacific Ocean. From the volcanoes of New Zealand through the islands of Indonesia and Japan, up through the Kamchatka Peninsula of Russia, across the Aleutian Islands of Alaska, and down through the Cascades of the Pacific Northwest, and the towering volcanic peaks of Central and South America. More than 400 active volcanoes strung together along the edges of the Pacific Plate like luminous beads on a vast dark necklace. A second type of volcano forms at the mid-ocean ridges, where tectonic plates pull apart and magma wells up continuously from the mantle below to fill the gap. These submarine volcanoes are the most numerous on Earth and among the most active, erupting almost constantly along the tens of thousands of kilometers of mid-ocean ridges that wind across the ocean floor. Most of their eruptions happen in complete darkness at depths of 2 to 3 kilometers, unseen and unheard by any surface creature. The lava that pours from them hits the cold seawater and freezes almost instantly into rounded shapes that geologists call pillow lavas, smooth, bulging forms stacked on top of one another like enormous dark cushions on the ocean floor. There is something deeply calming about that image. Miles beneath the ocean's surface, in perfect darkness, smooth, rounded pillows of black rock resting quietly on the seafloor, accumulated over millions of years of patient, unwitnessed eruption. The third type of volcano forms over what scientists call hot spots, places where an unusually hot column of mantle material, called a mantle plume, rises from deep in the interior and burns through the overlying plate like a blowtorch through thin paper. The Hawaiian Islands are the most famous example of hot spot volcanism. They are not located at a plate boundary. They sit in the middle of the Pacific Plate, far from any subduction zone or spreading ridge, formed by a single persistent plume of exceptionally hot mantle material that has been burning through the Pacific Plate for tens of millions of years. As the Pacific Plate moves slowly northwest over the fixed hot spot, new volcanic islands form over it and then drift away as the plate carries them beyond the plume's reach. The Big Island of Hawaii, which sits directly over the hot spot today, is the youngest and most volcanically active. To its northwest, the older islands of Maui, Molokai, Oahu, and Kauai represent earlier positions of the plate above the same hot spot, each one progressively older, lower, and more deeply eroded. Further still to the northwest, the chain continues as a series of submerged seamounts, ancient volcanic islands worn down by millions of years of erosion until they slipped beneath the sea. The Hawaiian island chain is a geological timeline written in volcanic rock, stretching across 1,500 miles of ocean, a record of a plate moving over a stationary source of heat, one island at a time. Over 70 million years, volcanoes have been foundational to the Earth in ways that go far beyond the landscapes they create. In the earliest days of the planet, volcanic activity was the primary source of the gases that formed the atmosphere: carbon dioxide, nitrogen, water vapor, sulfur dioxide, all exhaled by volcanoes from the deep interior, accumulating over hundreds of millions of years into the atmospheric envelope that made liquid water and eventually life possible. Every breath you take contains nitrogen that was, in some ancient chapter of Earth's story, released from the interior of the planet by volcanic activity. Volcanoes also contribute enormously to the fertility of the land around them. Volcanic soils are among the richest on Earth. The minerals carried up from the deep interior in volcanic rock, potassium, phosphorus, calcium, iron, whether out of the lava and ash over decades and centuries, enriching the surrounding soil with nutrients that support extraordinary agricultural abundance. The slopes of Vesuvius in Italy have been continuously farmed for thousands of years, despite the volcano's history, because the soil there is so extraordinarily productive. The same is true of the flanks of volcanoes in Java, in Central America, in the Pacific Northwest. Communities of people living close to mountains that could, in theory, threaten them, sustained by the extraordinary richness of the land those mountains have created. Life near a volcano is, in geological terms, a fair bargain. Some of the most dramatic volcanic events in Earth's history were not individual peaks, but vast outpourings of lava from long cracks in the crust called flood basalt provinces at several moments in geological history. Enormous quantities of lava poured from fissures in the earth over periods of hundreds of thousands or even millions of years, covering vast areas of land in layer upon layer of basalt. The Deccan traps in India, the Siberian traps, the Columbia River basalt group in the Pacific Northwest of North America. These are the remnants of ancient flood basalt events, now deeply eroded, but still recognizable as vast plateaus of layered dark rock. The largest of these flood basalt events released so much carbon dioxide and sulfur dioxide that they significantly altered the global climate, and some of them coincide in the geological record with mass extinction events. The Siberian traps eruption around 252 million years ago is associated with the largest mass extinction in Earth's history, the end Permian extinction, in which perhaps 90% of all marine species and and 70% of all land vertebrate species disappeared. Even in destruction, the earth was clearing the way for what came next. After each extinction, life recovered. Different, reshaped, but persistent. The same volcanic soils that smothered ancient ecosystems eventually nourished new ones. The same gases that altered ancient climates were eventually reabsorbed into rock and ocean, and the climate stabilized again. The earth is not fragile. It is extraordinarily, stubbornly resilient. Somewhere on Earth right now, a volcano is erupting. Perhaps a quiet lava flow on the slopes of Kilauea in Hawaii, moving slowly across old lava fields in the warm night air. Perhaps a submarine eruption along a mid-ocean ridge, unseen by any eye, building new ocean floor in the dark. Perhaps a low rumble of activity deep beneath a dormant peak, magma shifting in ancient chambers, the deep earth breathing in its sleep, the breath of the planet, steady and slow and ancient. Listen for it now in the quiet of your room, not with your ears, with something deeper, the faint, slow pulse of a living world beneath you, the warmth of deep rock miles below, radiating upward through stone and soil, and the floor beneath your bed. The earth is alive beneath you, and you are resting, quiet and warm on its surface. Let that warmth move through you now, up through the floor, through the bed, into your body, heavy and slow and deep, the deep earth breathing, and you breathing with it. Not a story told in words, or in pictures, or in any language we invented. A story told in texture and color and mineral composition. A story written in the arrangement of crystals, in the layering of sediment, in the faint impressions of ancient creatures pressed into stone hundreds of millions of years ago. Every rock you have ever picked up from a riverbank or turned over in a garden or felt beneath your feet on a mountain path. Every one of them carries a history longer and richer than anything written in any book. And the most beautiful thing about those stories is that they never truly end. Rock is not permanent. It only appears permanent on the scale of a human life. On the scale of geological time, rock is constantly moving through a great cycle, forming, transforming, breaking down, and forming again in a slow, patient circulation that has been running continuously for as long as the Earth has had a crust. Scientists call it the rock cycle, and it is one of the most elegant processes our planet has ever produced. It begins, as so many of Earth's stories do, with heat deep in the earth, under conditions of intense temperature and pressure. Rock melts into magma. This molten material moves slowly through the crust, rising toward the surface along fault lines and volcanic conduits, pushed upward by its own buoyancy and by the pressure of the mantle below. When it reaches the surface and erupts from a volcano, it is called lava. When it cools and solidifies, whether at the surface or while still deep underground, it becomes igneous rock. The word igneous comes from the Latin word for fire, rocks born of fire. When lava pours out at the surface and cools quickly in contact with air or water, it forms fine-grained rocks like basalt, the dark, dense rock of ocean floors and volcanic islands, its crystals too small to see without magnification, because the rapid cooling gave them almost no time to grow. When magma cools slowly deep underground, insulated by miles of surrounding rock, it forms coarse-grained rocks like granite, pale and speckled, its crystals large enough to see clearly with the naked eye, grown slowly over thousands of years in the quiet dark of the deep crust. Granite is the rock of the continents. The great continental cratons we visited in our Archean section are, at their ancient hearts, granite. If you have ever run your fingers across the surface of a granite countertop and felt those distinct speckles of white and gray and glittering black, you were feeling the individual crystals of quartz and feldspar and mica that grew slowly in the dark, miles underground, perhaps hundreds of millions of years ago. But igneous rock, once it reaches the surface, meets forces that will, in time, break it down entirely. The moment any rock is exposed at the Earth's surface, the slow process of weathering begins. Rain falls on it, slightly acidic from dissolved carbon dioxide, and begins the patient work of dissolving certain minerals. Water seeps into tiny cracks and freezes in winter, expanding as it does so, wedging the cracks a little wider each year. Wind carries particles of sand and grit that abrade the surface grain by grain. Roots of plants find the cracks and grow into them, prying them apart with a pressure that is gentle and unstoppable. Weathering is slow, and it is relentless, and it never rests. The broken fragments produced by weathering, from boulders down to sand grains, from sand grains down to the finest clay particles, are carried away by the agents of erosion. Water is the most powerful of these. Rain washes particles down hillsides into streams. Streams carry them to rivers. Rivers carry them in vast quantities toward the sea. The Mississippi River alone carries approximately 500 million tons of sediment to the Gulf of Mexico every year, enough to slowly extend the Louisiana coastline outward into the sea, depositing layer upon layer of material carried from the heart of a continent in quieter waters, in the still depths of a lake, in the sheltered shallows of a bay, on the gently sloping seafloor. Those particles settle. They drift downward through the water with the patience of snowflakes falling through still air, coming to rest in thin, quiet layers on the bottom, a layer of silt here, a layer of sand there, the remains of tiny marine organisms raining down from the sunlit surface waters above, accumulating in layers so thin that a year's worth of deposition might be measured in fractions of a millimeter. Year after year, layer after layer, century after century, and over time, as layers accumulate above, the weight of the overlying sediment begins to compress the deeper layers. Minerals precipitate from the water moving through the sediment, cementing the grains together. The loose sediment gradually, over millions of years, lithifies, turns to stone, sandstone, shale, limestone, mudstone. These are the sedimentary rocks, and they are the great recorders of Earth's history. Sedimentary rocks are the pages of the geological record. Their layers, called strata, are deposited in chronological order, oldest at the bottom and youngest at the top, like the pages of a book being written one at a time over millions of years. Embedded in those layers are the fossils of creatures that lived and died in the environments where the sediment accumulated. Shells and bones and tracks and burrows, all pressed into the stone, preserved by the slow chemistry of mineralization, waiting patiently for someone to come along and read them. The Grand Canyon is perhaps the most famous sedimentary record in the world. Its walls expose nearly 2 billion years of Earth's history in layered bands of color, red and orange and cream and gray, each layer a chapter, each color a different rock type, a different environment, a different moment in the long story of the American Southwest. Standing at the rim of the Grand Canyon and looking down into those layers is one of the closest things to time travel available to a human being. Your eyes can move through hundreds of millions of years simply by looking from the top of the canyon walls to the thin ribbon of river at the bottom. But the rock cycle does not end with sedimentary stone, because sedimentary rocks, too, are subject to the Earth's restless energy. When tectonic forces push sedimentary layers deep into the crust through subduction or through the collision of continents building mountain ranges, the rock encounters conditions of heat and pressure very different from those in which it formed. Under these new conditions, the minerals in the rock begin to recrystallize. The rock changes not by melting, but by transforming in the solid state, its structure reorganizing under heat and pressure the way a piece of wood might slowly change under sustained force. The rock becomes metamorphic rock, changed rock, transformed rock, limestone subjected to heat and pressure becomes marble, dense and crystalline. The rock of ancient temples and Renaissance sculptures, shale becomes slate, fine-grained and flat-cleaving, easily split into thin sheets. Sandstone becomes quartzite, incredibly hard and glittering. Its quartz grains fused under pressure into an almost impenetrable mass. Granite itself, subjected to enough heat and pressure, becomes nice, banded, and folded into those slow, graceful curves we glimpsed in the ancient Archean rocks of the Acasta Formation. And if the heat and pressure become intense enough, the metamorphic rock melts entirely back into magma, and the cycle begins again. Igneous rock, weathering and erosion, sedimentary rock, heat and pressure, metamorphic rock, deeper heat, magma, igneous rock. Around and around, over hundreds of millions of years, the material of the crust circulates through these forms, each one a different chapter of the same long story, each one bearing the marks of its own journey through heat and cold, pressure and release, depth and surface. The rock under your home has its own place in this cycle. It may be sedimentary, layers of ancient seafloor compressed into stone, or river deposits from a river that dried up before any human walked the earth. It may be igneous, cooled from ancient magma that rose through a long-vanished volcanic system. It may be metamorphic, changed by the heat of a mountain-building event that no creature alive witnessed. Whatever it is, it has been something else before, and it will be something else again, given enough time. Think of that as you rest here. The stone beneath you is on a journey, a slow, patient, circular journey that began before any life existed on this planet and will continue long after any life we can imagine. It is moving through the cycle right now, so slowly you will never feel it, but moving nonetheless. You are resting on something in motion, something ancient and patient and endlessly, quietly changing, like sleep itself, like the slow drift from waking into dreaming. One form dissolving gently into another. Let yourself follow the drift now. Let the stone carry you. If you have ever stood at the foot of a mountain and looked upward, you will know a particular feeling. It is not quite awe, though awe is part of it. It is not quite smallness, though you are very small in that moment. It is something older than either of those things. A deep, quiet recognition that you are standing next to something that has been here for a time so vast, it makes the word time itself feel insufficient. Mountains do not hurry. They do not move in any way you can perceive. They simply stand, patient and enormous and indifferent, their peaks trailing cloud, their lower slopes folded into valleys and ridges, and the slow green curves of foothills. And yet every mountain you have ever seen is, in geological terms, temporary. Every mountain is a moment, a frozen instant in a process that begins with the collision of plates and ends millions of years later with the quiet dissolution of stone into sediment and the long journey of that sediment to the sea. Mountains rise, mountains fall. The highest peaks on Earth today were, not so long ago in geological time, buried deep beneath younger rock or lying flat under an ancient sea. And the flat plains of today will, given enough time and the right movement of plates, become the mountain ranges of tomorrow. The building of a mountain range is called orogenesis, from the Greek words for mountain and origin, and it is one of the grandest, most prolonged performances in the entire repertoire of the Earth. When two continental plates collide, neither will yield easily. Continental crust, as we learned in our exploration of plate tectonics, is too light and buoyant to subduct into the mantle. So when continents meet, the crust has nowhere to go but up. The rock at the collision zone crumples and folds, thickening dramatically, piling layer upon layer of stone into ridges that rise higher and higher as the collision continues. It is a process of almost unimaginable slowness. The two plates pressing together at perhaps a centimeter or two per year, the mountains rising by a few millimeters annually. But over tens of millions of years, that accumulation of tiny increments builds peaks of extraordinary height. The Himalayas, as we touched upon before, are the supreme example of this process. 50 million years ago, the subcontinent of India, drifting northward across the ancient Tethys Sea, after splitting from the great southern landmass of Gondwana, finally made contact with the southern edge of the Eurasian plate. The collision has been ongoing ever since. The Indian plate is still driving northward at a rate of about 5 centimeters per year, and the Himalayas are still rising in response, their peaks inching upward against the patient, relentless work of erosion that is simultaneously wearing them down. It is a perfect geological standoff. The slow upward push of colliding continents balanced against the slow downward wearing of wind and water. The mountains exist in that balance. They are the visible expression of two enormous forces, one building and one destroying, meeting at the surface in a line of peaks and ridges and glaciated valleys. And the valleys themselves are as interesting as the mountains they lie between. Valleys form in many ways, each one telling a different story about the forces that shaped it. River valleys are perhaps the most familiar, carved by the patient, persistent work of flowing water, cutting downward through rock over millions of years. The river is always moving, always carrying a tiny amount of dissolved and suspended material away with it, always deepening its channel by the smallest, most imperceptible degree. With every passing season, a river valley in cross-section typically has a characteristic shape, wide at the top, narrowing toward the bottom where the river runs, its sides sloping at the angle at which the local rock weathers and erodes. Young river valleys, cutting quickly through resistant rock, are steep and narrow, V-shaped, as geologists describe them, with the river running swiftly between close rock walls. Old river valleys, where the river has been working for a very long time and has worn the surrounding rock down into gentle slopes, are wide and flat-floored. The river meandering slowly across its broad floodplain, barely seeming to hurry at all. The oldest river valleys have a peace about them that the youngest ones lack. They have had time to soften, time to fill with deep soil, to grow dense with trees and meadow grasses, to accumulate the quiet richness of millennia. The violence of their carving is entirely invisible, buried under the patient accumulation of life and soil and gentle landform. You would never guess, walking through a wide, old river valley on a quiet evening, that the landscape around you was carved by millions of years of relentless erosion. But perhaps the most dramatically beautiful valleys on Earth are not river valleys at all. They are glacial valleys. During the great ice ages, those long, cold periods when ice sheets spread across much of the northern hemisphere and alpine glaciers descended from mountain ranges across the world. Glaciers were among the most powerful erosive forces on the planet. A glacier is not simply ice. It is ice mixed with rock debris, pressing down under its own enormous weight, moving slowly downhill under gravity, scraping and grinding, and plucking at the rock beneath it with a force that no river can match. A river carves a V-shaped valley. A glacier carves a U-shape, wide, flat-floored, with steep, almost vertical walls rising on either side. The difference is dramatic and unmistakable. Yosemite Valley in California is a glacial valley. Its sheer granite walls, rising nearly a kilometer on either side of a flat, meadow-floored valley floor. The fjords of Norway and New Zealand are glacial valleys flooded by the sea after the ice retreated deep. Still, narrow inlets of extraordinary beauty, their dark water surrounded by walls of bare rock rising straight from the surface. The ice that carved those valleys retreated only about 12,000 years ago. In geological terms, this is essentially yesterday. The landscapes of Yosemite and the Norwegian fjords are freshly carved. The raw, clean work of ice that has only just departed. The rock still bearing the scratches and grooves left by the glacier's passage. The valley floors still barely beginning the slow accumulation of soil and vegetation that will, over millions of years, soften their young, sharp edges. Wind, too, is a sculptor of land, though a gentler one than water or ice. In dry environments, where there is little vegetation to hold the soil in place, wind carries sand particles that abrade exposed rock surfaces, polishing them smooth, carving hollows, isolating resistant rock formations into extraordinary shapes, the arches and spires and hoodoos of desert landscapes. The red rock country of Utah, with its gravity-defying towers and delicate arches of sandstone, was shaped partly by water working on rock that was laid down as ancient sand dunes 300 million years ago, then buried, then lithified, then slowly exhumed by erosion over millions of years beneath those arches and towers. The sand grains that make up the stone were once individual grains on an ancient desert floor, moved by a wind that blew 300 million years before any human breath was drawn. Every curve of that rock records a current of air that no living thing witnessed. Every layer tells of a season in an ancient desert that no creature alive today could imagine. And beneath all of these landforms, beneath the mountains and the valleys, the glacial fjords and the desert arches, the wide river plains and the steep young peaks, beneath all of it is the same patient rock cycle, turning slowly, material rising, being shaped, being worn down, being carried away, settling somewhere new, being compressed into stone, being carried deep, being transformed, rising again. The land is never finished. It is always in the middle of becoming something else, always partway between one form and the next, always in the slow process of being sculpted by forces that work so gradually they are invisible to any individual life. But lying here, in the quiet of this moment, you can feel it differently. You can let the mountains settle in your mind, not as fixed and permanent things, but as slow, patient processes, as frozen movement, as visible time. And you can let that understanding carry something of its own deep stillness into you. Because everything that is slow enough looks like rest, and everything that is patient enough looks like peace. The mountains are resting. The valleys are resting. The rivers are dreaming their way to the sea. And you are resting too, softly, completely, held by the patient, sculpted ancient land. Water is the most patient thing on earth, more patient than stone, more patient than ice, more patient even than the slow drift of continents across the face of the world. Because water does not need to hurry. It does not need to force anything. It simply finds the lowest point and moves toward it and keeps moving. And in doing so, It reshapes everything it touches, not through violence, but through the quiet, ceaseless application of time. There is a word for this quality in geology: persistence. And no force on the surface of this planet demonstrates persistence more completely or more beautifully than water. We have already followed the first rains falling on the young earth, filling the low places, gathering into the earliest oceans. We have watched those oceans deepen over hundreds of millions of years, covering perhaps as much as 90% of the early Earth's surface beneath their warm, mineral-rich waters. Now let us rest with water more slowly. Let us follow it through its quieter work, not the dramatic birth of oceans, but the daily, ordinary, extraordinary movement of water across and through the surface of the world. The ocean covers approximately 71% of the Earth's surface today. Its average depth is about 3,688 meters, nearly 4 kilometers from surface to floor. At its deepest point, the Challenger Deep in the Mariana Trench of the Western Pacific, the ocean floor lies almost 11 kilometers below the surface. If you could place Mount Everest in the Challenger Deep, its summit would still be more than 2 kilometers beneath the waves. The ocean is not one thing. It is a world within a world, layered, moving, alive, and ancient. Its surface waters are warmed by the sun and stirred by the wind into waves and currents. Its deep waters are cold and still and dark, moving in vast, slow currents driven by differences in temperature and salinity, circulating around the planet on timescales of hundreds or even thousands of years. The great ocean circulation, sometimes called the ocean conveyor belt, or more formally, the thermohaline circulation, is one of the most important and least visible processes on Earth. It begins in the cold polar seas, where surface water chilled by the Arctic and Antarctic winters becomes dense enough to sink toward the ocean floor. That cold, dense water creeps slowly along the bottom of the ocean, flowing from the polar regions toward the equator in a journey that takes centuries. Meanwhile, warmer surface water flows in the opposite direction replace it, carrying heat from the tropics toward the poles, moderating the climates of entire continents. The Gulf Stream, which carries warm tropical water northward along the eastern coast of North America and across the Atlantic toward Europe, is part of this great circulation. It is the reason that the British Isles and Norway enjoy climates far milder than their northerly latitudes would otherwise allow. The warmth you feel on a mild winter day in much of northern Europe is, in part, warmth carried by water from the Caribbean, flowing in a current that has been running for millions of years. The ocean breathes in its own slow way, and its breath warms the world. Below the sunlit surface waters, the ocean grows darker and colder with every meter of depth. At around 200 meters, sunlight fades to a permanent twilight. Below 1,000 meters, there is no light at all. Only the profound, absolute darkness of the deep ocean, where the pressure is hundreds of times greater than at the surface, where the temperature hovers just above freezing, and where life, extraordinary, adapted, strange life, still finds a way to exist. In the deep ocean trenches, communities of organisms cluster around hydrothermal vents. Cracks in the ocean floor, where superheated, mineral-rich water jets upward from the volcanic heat below. These vent communities live entirely without sunlight, powered not by photosynthesis, but by chemosynthesis, extracting energy from the chemical reactions between the vent water and the surrounding sea. Tube worms 2 meters long, ghostly white crabs, translucent shrimp, communities of life built around the deep earth's own heat in permanent darkness at crushing pressure, miles from the surface. Life does not give up easily on this planet. It finds every warm crack, every chemical gradient, every improbable niche, and it settles there and grows. But let us rise from the deep ocean now and follow water on its other great journey. Let us follow it inland. When the sun warms the ocean's surface, water evaporates, lifted into the atmosphere as invisible vapor, rising on warm air currents, carried by wind hundreds, and sometimes thousands of miles inland. As it rises and cools, it condenses back into tiny droplets, forming clouds. And eventually, it falls again as rain or snow, landing on mountains and plains and forests and deserts, beginning the long journey back to the sea. This is the water cycle. And like the rock cycle, it has been running without interruption for nearly 4 billion years. Rain falling on a mountain does several things simultaneously. Some of it runs off immediately, gathering into thin sheets on bare rock and flowing downhill toward the nearest stream. Some of it soaks into the soil, drawn downward through the earth by gravity, moving slowly through the spaces between soil particles and through the cracks in rock, eventually collecting in underground aquifers, vast, slow reservoirs of groundwater that may have taken hundreds or thousands of years to accumulate. And some of that water reaches a stream. The stream reaches a river, and the river begins one of the most quietly dramatic journeys in all of nature, the long, patient passage from mountain to sea. A river is never the same twice. Its character changes completely along its length. High in the mountains, where the gradient is steep and the water moves swiftly, a river is loud and restless, tumbling over boulders, carving channels in bare rock, picking up the sand and gravel that will travel with it all the way to the sea. The water is cold and clear and full of energy, catching the light in white foam and fast surface ripples. As the river descends into lower country and the gradient lessens, its character changes. The current slows. The river widens. It begins to meander, swinging in long, lazy curves across its floodplain, depositing material on the inside of its bends, and slowly eating away at the outside. Over time, these meanders migrate across the floodplain, the river shifting gradually sideways, as well as moving forward, carving a wide swath through the valley floor. Old rivers meander most beautifully. The Mississippi, the Amazon, the Nile in its lower reaches. These great rivers move through their floodplains in sweeping, oxbow curves of extraordinary grace, their banks thick with vegetation, waters brown with the sediment of an entire watershed carried patiently toward the sea, flying over a great river delta from above. You can see the fractal geometry of countless distributary channels spreading out across flat land like the branches of a tree or the veins of a leaf, depositing their cargo of sediment grain by grain into the waiting sea. The Nile carries the soil of Central Africa to the Mediterranean. The Amazon carries the soil of South America to the Atlantic. The Ganges carries the soil of the Himalayas to the Bay of Bengal. Every great river is a bridge between the high places and the deep water. A slow, continuous conversation between mountains and ocean, mediated by the patient, unhurried movement of water. And in the ocean, what those rivers carry settles slowly to the floor. Layer upon layer of sediment, accumulating in the quiet dark of the deep water. The same sedimentary process we visited in our exploration of the rock cycle, the material of eroded mountains becoming the material of future stone. The cycle continuing as it always continues, without hurry and without end. Water connects everything on this planet. It moves between ocean and cloud and rain and river and groundwater and glacier and back to the ocean, carrying minerals and heat and life wherever it goes. It carved the Grand Canyon. It built the Mississippi Delta. It filled the fjords of Norway with still, cold beauty. It delivered the first building blocks of life to the early Earth's warm, shallow seas. Water is the medium through which the Earth's great stories are told, and water, in its quietest form, is what you are mostly made of. The same water molecules cycling through your body tonight may have traveled through an ancient river, rested in a deep ocean, fallen as rain on a mountain that no longer exists, been part of a glacier, risen as vapor into a cloud above a sea your ancestors never saw. You are part of the water cycle too, part of the great, patient, endless circulation. So let yourself feel that now. The slow, soft movement of water through you, through your breath, through the quiet tide of your bloodstream, moving with the same patience it has always moved with seeking the lowest, quietest place, which is exactly where you are, drifting now, softly, like water finding still ground. There is a particular kind of silence that comes over a person when they truly reckon with geological time. Not the comfortable silence of a quiet room or the peaceful silence of a night without wind. Something deeper than that, the silence of a mind that has momentarily grasped something so vast, so far beyond the ordinary scale of human experience, that ordinary thought simply stops for a moment. The way your eyes might stop adjusting when you step from bright sunlight into a very dark room. A pause, a stillness, a sense of the ground shifting gently beneath everything you thought you understood about the word old. Geological time does that to a person, and it is one of the most quietly beautiful sensations available to a curious mind. We use a phrase for it, deep time, coined by the writer John McPhee in the 1980s, borrowed and embraced by geologists and science writers. And anyone who has ever stood in front of an exposed cliff face and tried to count the layers, deep time is not just a large number. It is a different relationship with time altogether. It is the recognition that the universe and this earth have been doing their slow, patient work for so long that human history, all of it, from the first stone tools to the present moment, occupies a sliver so thin at the end of the geological record that it is, in most representations, literally invisible. The geological timescale is the framework scientists use to organize and navigate deep time. It is a calendar of the earth, a structured sequence of eons and eras and periods and epochs, each one defined by the rock record and the fossils preserved within it, each one separated from the next by some significant change in the character of life or the composition of the Earth's crust. The largest divisions are the eons. We have already visited 2 of them in our journey tonight. The Hadean, Earth's fiery infancy, and the Archean, the age of first rocks and first life. Following the Archean came the Proterozoic Eon. The name means earlier life, spanning from 2.5 billion years ago to 541 million years ago, another immense chapter, nearly 2 billion years long, during which oxygen slowly accumulated in the atmosphere. The first complex cells with nuclei appeared. The first multicellular organisms emerged, and the continents drifted through configurations utterly unlike anything on a modern map. And then, 541 million years ago, something happened that so dramatically changed the fossil record that geologists drew a bold line in the stone and called it the beginning of a new eon entirely, the Phanerozoic Eon, the eon of visible life. At its very beginning, in what geologists call the Cambrian explosion, complex multicellular animal life diversified with astonishing speed within a geologically brief span of perhaps 20 million years. Nearly all the major body plans of animals that exist today appeared in the fossil record for the first time. Creatures with eyes and limbs and shells and segmented bodies, predators and prey. Creatures filtering the water for nutrients, and creatures actively hunting other creatures through ancient seas. 20 million years sounds like a long time, and in human terms, it is incomprehensible, but on the geological timescale, it was genuinely rapid. A sudden flowering of biological complexity after 3 billion years of microbial life. The earth had been patient for so long, and then, seemingly all at once, it burst into the extraordinary diversity of animal form. We read all of this in rock, in the patient layering of sedimentary stone, in the fossils pressed into those layers, in the chemical signatures of ancient atmospheres trapped in minerals, in the magnetic stripes of ocean floor basalt. The rock record is the Earth's own diary, written continuously for 4 billion years in a language that took humanity the better part of 2 centuries to learn to read. The man most responsible for establishing the principles of that reading was a Scottish farmer and physician named James Hutton, working in the late 18th century. Hutton spent years studying the rocks of the Scottish countryside, the layered sedimentary cliffs, the eroded coastlines, the slow accumulation of river sediments. And from all of that observation, he arrived at a profound and beautifully simple idea. The present is the key to the past. What Hutton meant was this: the geological processes operating today, the erosion of riverbanks, and the deposition of sediment, and the slow weathering of stone, are the same processes that have always operated if you know how fast sediment accumulates in a modern river delta. You can estimate how long it took to accumulate a given thickness of ancient sedimentary rock. If you understand how lava cools today, you can read the cooling history of ancient volcanic rocks. The present and the past are written in the same language. Hutton called his principle uniformitarianism, and it transformed geology from a descriptive exercise into a genuinely historical science. For the first time, the Earth had a history, not just a structure, but a story with a sequence, a direction, a before and after. And when Hutton looked at the vast thicknesses of sedimentary rock exposed in the cliffs and riverbeds around him, and applied his principle to estimate how long they had taken to form, he arrived at a conclusion that startled even himself. He wrote that in the geological record, he could find no vestige of a beginning, no prospect of an end. The Earth, he understood, was ancient far beyond any measure then available to science, not thousands of years old, as most of his contemporaries believed, but something else entirely, something deep. He was right, of course, though even Hutton could not have imagined quite how deep. It was not until the 20th century, with the development of radiometric dating, that scientists could put precise numbers on geological time. Radiometric dating uses the known decay rates of radioactive elements locked within minerals. Uranium decaying to lead, potassium decaying to argon, carbon decaying in its own shorter rhythm for younger materials. As clocks built into the rock itself, the radioactive element begins decaying the moment a mineral crystallizes from magma or is deposited from solution. And because the decay rates are constant and precisely known, the ratio of parent to daughter isotope in a sample tells you exactly how long ago that crystallization occurred, a clock built into stone, running continuously without any mechanism, powered only by the laws of physics. From the moment the rock formed until the moment a geologist removes a sample and measures it in a laboratory with radiometric dating, the age of the Earth was established at approximately 4.54 billion years, a number refined over decades of measurement from rocks, meteorites, and lunar samples, until it is now known with remarkable precision 4,540 million years, a number so large that even writing it in full feels almost ceremonial. To help make that number feel slightly more approachable, scientists and writers have long used the device of the cosmic calendar, imagining the entire history of the Earth compressed into a single year, each month representing roughly 375 million years. On this compressed calendar, the Hadean and the formation of the oceans occupy the first month or two of January. The Archean stretches through the late winter and spring. The first complex cells appear sometime in late summer, the Cambrian explosion, that great flowering of animal life, happens in mid-November. The dinosaurs appear in mid-December and are gone by the day after Christmas, all of human history. Everything from the first stone tools through ancient Egypt and Greece and Rome, through the Middle Ages and the Renaissance and the Industrial Revolution, and everything that has happened since fits into the last 17 seconds of the 31st of December. 17 seconds. Let that sit with you for a moment, gently, without alarm, because there is something deeply peaceful in it if you let it be peaceful. The brevity of human history against the backdrop of geological time does not diminish us. It simply places us. It reminds us that we are part of something ancient and enormous and ongoing, something that was here long before us and will continue long after, something patient and deep and continuous. We are not separate from geological time. We are inside it. Right now, in this moment, you are living in the Holocene epoch, a warm interglacial period that began about 11,700 years ago. At the end of the last ice age, geologists have recently proposed a new epoch, the Anthropocene, to mark the period in which human activity has become a significant force, shaping the rock and atmosphere and biology of the Earth. Whether that name becomes formally adopted or not, the idea behind it is geological in the truest sense. We are part of the record. Our time here will leave a layer in the stone to be read by whatever intelligence comes after us, in whatever deep future awaits. That is a thought worth holding gently. We are, right now, writing a page in the Earth's long diary. Our cities and our roads and our altered atmosphere and our plastic and our cultivated soils. All of it will leave some trace in the geological record, some thin and readable layer, pressed between the chapters of a story that stretches back 4.5 billion years and forward into a future no mind alive can fully imagine. We are part of the ancient diary, one slow, quiet line written in the language of stone and time. And for now, in this moment, you can set that pen down. You can rest in the deep time, float in it, the way a stone floats in the slow current of a river, not moving, just held, just carried, just resting in the long, patient flow of everything. There is so much time. There is no hurry at all. Let your eyes grow heavy with the weight of it. 4 billion years of quiet, pressing down as gently as deep water, holding you still. Breathe slowly. Drift. Imagine the world growing cold. Not the cold of a winter morning, sharp and brief, retreating by afternoon into something milder. A deeper cold than that, a cold that arrives so slowly you would never feel it arriving. A fraction of a degree over a century. A slight thickening of the winter snowpack that does not entirely melt by summer. A glacier at the head of a mountain valley that advances year by year, just a little further down the slope than it did the year before. A cold that takes 10,000 years to fully arrive, and then stays for 100,000 more. This is the rhythm of an ice age, not a sudden catastrophe, not a dramatic event, but a long, slow, planetary exhale, the Earth cooling gradually, the ice sheets thickening and spreading outward from the poles, the sea levels dropping as more and more of the world's water is locked up in ice rather than flowing freely in the ocean, a pulse, a slow, deep, rhythmic pulse of cold and warmth that has been beating through the Earth's climate system for hundreds of millions of years. We are, right now, technically living in an ice age. This surprises many people, but the definition of an ice age in geological terms is simply a period during which permanent ice sheets exist somewhere on the Earth's surface, and both Greenland and Antarctica are currently covered by permanent ice sheets of enormous thickness. By that definition, the current ice age began about 2.6 million years ago, at the start of a geological epoch called the Pleistocene, and it has not yet ended. What we call ice ages in the more familiar, popular sense. The periods of mammoth and woolly rhinoceros, of vast glaciers covering northern Europe and North America, of sea levels 100 meters lower than today, are technically called glacial periods. They are the cold pulses within the larger ice age, and between them, warmer periods called interglacials have allowed the ice to retreat, the sea levels to rise, and life to expand back into the newly uncovered land. We are currently living in an interglacial period called the Holocene, which began about 11,700 years ago, when the last great glacial period ended, and the ice sheets that had once covered much of North America and northern Europe began their long, slow retreat, all of recorded human history. Every civilization, every empire, every city ever built, every field ever planted, has taken place within this single interglacial. The warmth and stability of the Holocene climate is not the planet's default setting. It is a window, a particular, relatively benign phase within a much longer cycle of cold and warm, advance and retreat, freezing and thawing. The discovery of this rhythm, the understanding that the Earth's climate has pulsed regularly between glacial and interglacial states, is one of the great detective stories of modern science, and the key was found not in rock, but in the sky in the early 20th century. A Serbian mathematician named Milutin Milankovic spent years calculating by hand the subtle variations in the Earth's orbit and axial tilt that occur over long cycles of time. The Earth's orbit around the Sun is not perfectly circular. It stretches into a slightly more elliptical shape and then rounds back toward circular on a cycle of about 100,000 years. The tilt of the Earth's axis varies between about 22 and 24.5 degrees on a cycle of about 41,000 years, and the direction in which the Earth's axis points, like the wobble of a spinning top, traces a slow circle over a period of about 26,000 years. Each of these cycles, individually, produces only a small change in the amount of sunlight reaching different parts of the Earth's surface at different times of year. But when all three cycles align in ways that reduce the amount of summer sunlight reaching the northern hemisphere, when summers in the north become just cool enough that the previous winter's snow does not entirely melt before the next winter arrives, ice begins to accumulate, and once ice begins to accumulate, it reflects more sunlight back into space, which cools the climate further, which allows more ice to accumulate in a slow, self-reinforcing cycle that can, over thousands of years, grow into a full glacial period. This is what scientists call a positive feedback loop, and the astronomical cycles that trigger it are known as Milankovic cycles, a beautiful name for a beautiful idea. The ice ages are not random. They are not accidents. They are the predictable, rhythmic response of a complex climate system to the slow, geometrical variations in the Earth's orbit and tilt. The pulse of the ice ages is driven, ultimately, by mathematics. The evidence for this rhythm is written in some of the most extraordinary archives science has ever found. In Antarctica and Greenland, glaciologists have drilled deep into the ice sheets, pulling up cores of ice that preserve, layer by layer, a continuous record of the Earth's climate, stretching back hundreds of thousands of years. Each annual layer of ice traps tiny bubbles of the atmosphere, as it was when that layer formed. A sealed sample of ancient air, preserved in perfect cold and darkness, waiting to be read from those bubbles. Scientists can measure the concentration of carbon dioxide and other greenhouse gases in the ancient atmosphere. From the ratio of oxygen isotopes in the ice itself, they can calculate the temperature at the time each layer formed. The result is a detailed, continuous climate record, a graph of temperature and greenhouse gas concentration going back 800,000 years, showing the rhythm of glacial and interglacial cycles with extraordinary clarity. The pattern is unmistakable. Cold glacial periods lasting roughly 100,000 years, punctuated by warm interglacials of 10 to 30,000 years, repeating in a slow, regular rhythm, driven by those Milankovic cycles, 8 complete cycles in the last 800,000 years alone, each one a slow pulse of the planetary climate, expanding ice, then retreating, sea levels falling, then rising, ecosystems shifting, then shifting back during the depths of the last glacial maximum. About 20,000 years ago, the ice sheets covering North America were in some places more than 3 kilometers thick. The weight of that ice was so enormous that it pressed the rock of the continent downward by hundreds of meters. And those rocks are still slowly rebounding upward today. Now that the ice has been gone for 12,000 years, Scandinavia is rising at several millimeters per year, still recovering from the weight of ice that melted millennia ago. The land remembers. Stone remembers. Even now, the earth is still adjusting to the last ice age. The landscapes left behind by the retreating glaciers are among the most beautiful on Earth. The Great Lakes of North America were carved by glacial erosion and filled by glacial meltwater. The gentle, rounded hills of the English countryside were shaped by glacial deposition, till and moraine left behind as the ice retreated. The extraordinary system of lakes in Finland, tens of thousands of them, scattered across the landscape like fragments of a broken mirror. Occupy basins scraped out by the glacier and filled with the clearest meltwater everywhere the glaciers went. They left a quieter, softer landscape behind them. Rock smoothed and rounded by the passage of ice. Valleys widened and deepened. Soils enriched by the fine rock flour ground from the bedrock by the glacier's passage. A flour so fine and mineral-rich that it nourishes some of the most productive agricultural land in the world. The cold came, and when it left behind gifts. Beyond the Pleistocene ice ages, the geological record reveals older glaciations of even greater extent. About 700 million years ago, during what scientists call the Cryogenian period, the Earth may have frozen almost entirely. Ice sheets extending from the poles to near the equator, the oceans covered, the world white and still and sealed beneath ice kilometers thick. This extraordinary event, known informally as Snowball Earth, lasted perhaps millions of years before volcanic carbon dioxide built up sufficiently in the atmosphere to trigger a rapid warming and release the planet from its ice. Even that deep freeze ended. Even the most extreme cold the Earth has ever known eventually gave way to warmth. The planet has always found its way back to liquid water, back to open ocean, back to the conditions that life requires. The Earth is resilient in a way that is almost comforting once you understand it. Not fragile, not easily broken. A system so large, so old, so full of slow, self-correcting feedbacks and balances that it has survived every catastrophe its long history has produced and emerged eventually into something livable again. Think of that resilience now as you lie here in the warm quiet. You are resting in an interglacial, in one of the warm, generous pauses between cold chapters, a window of mild and stable climate that has lasted 12,000 years and sustained everything you know. You are held in that warmth as surely as the ice holds its ancient bubbles of air, safe and warm and held. The cold is far away, is quiet, and the long pulse of the ice ages moves too slowly to feel. A rhythm so deep and slow, it is closer to a heartbeat heard from underwater than anything your waking mind can follow. Follow it now, downward, into the warm and the still and the deep. Deep in the earth, in the dark and the heat, and the extraordinary pressure of the planet's interior, something is growing. Slowly, atom by atom, layer by invisible layer, a crystal is forming in the dark, building itself according to rules so precise and so ancient that they were written into the fabric of matter long before the earth itself existed. No hand guides it. No eye watches it. There is no light at all where this is happening. Only heat and pressure, and the patient chemistry of elements arranging themselves into the most orderly, most geometrically perfect structures that nature produces. A crystal is geometry made solid. It is mathematics you can hold in your hand, and the world beneath your feet is full of them. Minerals are the fundamental building blocks of rock. Every rock you have ever touched, every granite countertop, every sandstone cliff, every smooth river pebble is made of minerals. And every mineral is a crystal, or a collection of crystals, its atoms arranged in a precise, repeating three-dimensional pattern that extends through the entire solid, from one surface to the other, without interruption and without variation. There are approximately 5,000 known minerals on Earth. 5,000 distinct combinations of elements, each one with its own internal geometry, its own crystal structure, its own characteristic hardness and color and luster and cleavage, each one a unique solution to the chemical and physical conditions under which it formed. Each one a record locked in geometry of a particular moment and place in the history of the earth. The most abundant minerals in the earth's crust are the silicates, compounds built around the silicon-oxygen tetrahedron, a tiny pyramid of one silicon atom bonded to 4 oxygen atoms that serves as the fundamental structural unit of most of the rock on Earth's surface. Quartz is a silicate, that clear, glassy mineral you find in granite and sandstone and river gravel, hard enough to scratch glass, its crystals growing in hexagonal columns that taper to a perfect six-sided point when conditions allow them to grow freely. Feldspar is a silicate and the most abundant mineral in the crust. The white and pink grains in granite, the milky crystals in 1,000 varieties of rock. Mica is a silicate, growing in thin, flexible sheets that split apart in perfect planes, glittering with a soft silver or golden luster when you turn them in the light. Olivine is a silicate, green and glassy, abundant in the mantle beneath the crust, occasionally carried up to the surface in volcanic rock. These common minerals are the quiet, workmanlike materials of the everyday geological world, not glamorous, perhaps, but each one is a crystalline wonder at the atomic scale, a three-dimensional lattice of atoms bonded together with extraordinary precision, repeating the same pattern millions of times across the volume of every tiny grain. And then there are the rarer minerals, the ones that form under unusual conditions in unusual places, where the chemistry is just right and the time is long enough and the conditions remain stable enough for truly extraordinary crystals to grow. In the caves of Naka, in the Chihuahuan Desert of northern Mexico, miners in the year 2000 discovered a chamber that no human eye had ever seen. They called it the Cave of Crystals, and inside it, growing from the floor and ceiling and walls of a cave that had been sealed and flooded with mineral-rich water at a constant temperature for hundreds of thousands of years, were crystals of selenite, a form of the mineral gypsum, of a size that seemed to belong to another world entirely. The largest crystals in the Cave of Crystals are 12 meters long, longer than a city bus, 1.5 meters thick, translucent, milky white, glowing softly in any light that touches them. Enormous, smooth, geometrically perfect columns of crystal, growing from the cave floor and jutting from the walls and arching across the ceiling in slow, massive curves. They grew at a rate of perhaps 1 centimeter every 1,000 years, in complete darkness, in water at a temperature of 58 degrees Celsius over a period of perhaps 500,000 years, entirely alone, entirely patient, building themselves atom by atom into something of breathtaking size and beauty, with no audience and no purpose except the pure chemistry of their own making. That is what time and patience and the right conditions produce in the quiet dark of the deep earth. The conditions under which minerals form are as varied as the minerals themselves. Some grow from magma cooling slowly deep underground. The feldspars and quartz and mica of granite, taking thousands of years to crystallize from a slowly cooling melt. The slower the cooling, the larger the crystals in some rare rock formations called pegmatites, where pockets of water-rich magma cool exceptionally slowly. Crystals of extraordinary size can form. Feldspar crystals the size of a house have been found in some pegmatite deposits, grown over millions of years in the heat of the deep crust. Some minerals form from water. Hot, mineral-rich water circulating through cracks in the rock dissolves certain elements and carries them in solution until a change in temperature or pressure causes them to come out of solution and crystallize on the walls of the crack. This is how many of the world's most beautiful gemstones form. Amethyst, purple quartz, growing in geodes, hollow rock cavities lined with crystals that point inward toward the center, like the petals of an impossible stone flower. Calcite forming stalactites and stalagmites in limestone caves, building elaborate curtains and columns, and delicate straws of mineral from the drip of mineral-laden water over thousands of years. Gemstones are simply minerals whose beauty, durability, and rarity have caught the human eye. A diamond is carbon, the same element as the graphite in a pencil, but carbon that has been subjected to the extraordinary pressures of the deep mantle, more than 150 kilometers below the surface, and crystallized there into the hardest natural material on Earth. The carbon in a diamond was pressed into that crystal structure at depths we will never reach, in conditions of heat and pressure that exist nowhere on the surface, and then carried upward to the crust in explosive volcanic pipes called kimberlites, erupting from the deep mantle like messages from an inaccessible interior. Every diamond is a piece of the deep earth, brought to the surface by an ancient volcanic eruption. Every diamond is a traveler from a place no human will ever visit. Ruby and sapphire are the same mineral, corundum, aluminum oxide, colored differently by trace impurities. Iron and titanium give sapphire its blue. Chromium gives ruby its deep, warm red, a trace of an element, present in quantities too small to weigh, producing a color so rich and vivid that humans have treasured it for thousands of years. The color of a ruby comes from an atom of chromium sitting in the crystal lattice where an aluminum atom would normally be. A substitution so small it is invisible at any scale larger than the atomic, producing a result visible from across a room. Emerald is beryl-colored green by chromium and vanadium. Turquoise is a phosphate of copper and aluminum. Its blue-green color, the pure expression of copper's chemistry. Malachite, that deep, banded green stone, is copper carbonate, the same copper in a different molecular arrangement, producing a completely different crystal form and color. The same element rearranged becomes something entirely new. This is the quiet magic of mineralogy. The same handful of elements, silicon, oxygen, aluminum, iron, calcium, magnesium, sodium, potassium, and a few others, rearranged in different geometries, under different conditions, produce the entire astonishing variety of minerals that make up this planet. The same atoms, the same rules, the same patient chemistry, but an almost infinite variety of outcomes, each one beautiful in its own way, each one a record of the conditions and time in which it formed. The earth is a crystallographer of incomparable skill and patience. It has been arranging atoms into minerals for 4.5 billion years, under every conceivable combination of temperature and pressure and chemistry, producing 5,000 distinct solutions, and undoubtedly many more we have not yet found. And right now, somewhere in the deep crust beneath you. That work is continuing. Minerals forming in the slow cooling of deep magma. Crystals growing in the hot water, circulating through cracks in the rock. Atoms finding their places in lattices that will persist, unchanged and undisturbed, for millions of years to come. The geometry of the deep, working quietly in the dark, building as it always has, something patient and precise and beautiful. Let that image rest with you now, the deep, quiet crystal growing in the dark. Each atom settling softly into its place in the lattice, one by one, in perfect order, in absolute stillness. No hurry, no noise, just the slow, perfect geometry of matter finding its most stable, most beautiful form. You are that still. You are that ordered. Everything in you settling right now into its most natural and restful arrangement, atom by quiet atom, breath by slow breath, crystal clear and perfectly still. Somewhere in a layer of gray limestone, pressed between two plains of ancient rock that have not been separated since the Devonian period, 370 million years ago, there is a shell. It is a perfect shell, coiled and ridged and exquisitely detailed. Every chamber of its spiral interior preserved in stone. Every subtle surface texture captured in mineral as faithfully as a photograph. The creature that made it lived in a warm, shallow sea, in a world so different from this one that you would not recognize a single landmark. It breathed and moved and fed and died and sank slowly to the seafloor and was covered by sediment and was, over millions of years, turned to stone. And it has been waiting ever since in the quiet dark of the rock. This is what a fossil is. Not a bone exactly, though bones are among the most common things fossilized. A fossil is the preserved evidence of ancient life. A record left in rock by an organism that lived and died long before any human eye existed to see it. Shells and bones and teeth and wood, footprints pressed into ancient mud and hardened into stone. The burrows of worms in Cambrian seafloor sediment. The delicate impression of a feather in fine-grained limestone, a raindrop pattern on a Precambrian mudflat, preserved for 500 million years. The conditions required to make a fossil are surprisingly specific, which is why fossils are far rarer than the abundance of ancient life would suggest. When a creature dies, the most likely outcome is decomposition. Bacteria and scavengers, and the slow chemistry of exposure returning every organic molecule back to the earth to become a fossil. A creature needs to be buried quickly before decomposition runs its course. A sudden flood of sediment, a fall to the bottom of a still, oxygen-poor lake where nothing can decompose, a flow of volcanic ash, sealing everything it touches in a perfect, airtight layer. Burial is the first gift the earth gives to a creature that will become a fossil. Once buried, the slow process of mineralization begins. Water percolating through the sediment carries dissolved minerals, silica, calcium carbonate, iron compounds, into the spaces within the buried bone or shell. Over thousands and sometimes millions of years, those minerals precipitate out of solution, filling the tiny pores and cavities of the original material, replacing the organic matter molecule by molecule with stone. The shape is preserved perfectly. The chemistry is entirely replaced. The creature is gone. The record of the creature remains. Some of the most extraordinary fossils ever found preserve not just hard shells and bones, but the soft tissues that almost never survive the fossilization process. In the Burgess Shale of British Columbia, a deposit of fine-grained mudstone laid down approximately 508 million years ago during the Cambrian period. The soft bodies of ancient marine animals are preserved in exquisite detail. Creatures without shells, without bones, animals made of nothing but soft tissue that would normally vanish within days of death, preserved here in flattened carbon film impressions of extraordinary delicacy. The Burgess Shale is one of the most precious geological sites on Earth. Its fossils are our clearest window into the world of the Cambrian explosion. That extraordinary moment when animal life first diversified into the vast variety of body plans that still underlies all animal life today. Creatures with 5 eyes, creatures with circular mouths lined with teeth arranged in spirals, creatures whose body plans match nothing alive today, belonging to lineages that tried their particular solution to the problem of living, and then quietly disappeared. The fossil record is full of these quiet disappearances. For every lineage that survived to the present day, there are many more that flourished for millions of years and then were gone. Not dramatically in most cases, but simply fading from the record, their last representatives dying one by one until none remained. The rock holds them all equally, the successful and the vanished, the brief and the enduring, all pressed into the same patient stone. Paleontologists, the scientists who read the fossil record, describe their work as detective work, and it is. Every fossil is a clue, but the clues are incomplete, and the picture they build is always partial, always provisional, always subject to revision when a new quarry opens or a new specimen is found. The fossil record is not a complete archive. It is more like a library from which most of the books have been lost, leaving only fragments, a page here, a chapter there, from which the patient reader must reconstruct the whole. And yet what those fragments reveal is extraordinary. The evolution of the vertebrate eye, traced through hundreds of millions of years of fossils. The slow development of the mammalian inner, ear from bones that were once part of the reptilian jaw. The gradual, beautiful transition of a 4-limbed land animal back into the ocean over 50 million years, becoming eventually a whale. The rock remembers all of it, quietly, without judgment or preference. Every creature that ever lived and died near sediment that could preserve it left some trace, however faint, in the long stone record of this world. Tonight, as you lie here in the quiet, somewhere beneath the ground below you, perhaps nearby, perhaps very far, there are fossils resting in the dark, shells and bones and impressions of creatures that lived their full lives in worlds you will never see. preserved in stone, patient and perfect and still. They have been resting there in their own kind of sleep for millions of years. Rest with them now, quiet and still and held in the dark. Between the rock and the sky, there is a layer so thin and so ordinary that most of us walk across it every day without a thought. Soil. Not dirt, though we use the words interchangeably. There is a distinction worth making. Here in the quiet, dirt is simply displaced soil. Soil is something far more extraordinary. Soil is alive. It is one of the most complex, most diverse, most biologically rich materials on the surface of the earth. A living fabric stretched across the land in a layer that averages perhaps 1 meter in depth, sometimes less, rarely more. If the earth were a peach, the soil would be thinner than the skin. And yet, without it, almost nothing you know would exist. Soil takes a very long time to form. This is perhaps its most important and least appreciated quality. On bare rock, under the patient influence of rain and temperature, and the slow chemistry of air, the process of soil formation, pedogenesis, from the Greek word for earth and the word for origin, begins with nothing but mineral and time. It begins with weathering. Rain dissolving the surface of the rock. Freeze and thaw cycles, opening cracks. Wind carrying grit that abrades exposed surfaces, grain by grain. The rock breaks down slowly into smaller and smaller fragments: gravel, sand, silt, clay, each one a different size of the same basic material. Crushed and chemically altered rock, stripped of its crystalline structure, reduced to loose particles that water can move through and roots can penetrate, but particles of crushed rock alone are not soil. They are the mineral skeleton of soil, the foundation on which something far richer will eventually be built. For rock particles to become soil, something else must arrive. Life must arrive. The first pioneers on bare rock are almost always the most patient and the most overlooked of living things. Lichens, those flat, crusty, gray-green organisms you find on exposed rock surfaces, in every climate on Earth are not a single organism, but a partnership between a fungus and a photosynthetic alga, living together in a relationship so ancient and so stable it has persisted for hundreds of millions of years. Lichens produce weak acids that slowly dissolve the rock surface beneath them, extracting minerals for their own growth, and in doing so, accelerating the weathering of the rock. When lichens die, their thin organic residue adds the first microscopic traces of organic matter to the mineral surface. Mosses follow, taking hold in the thinnest possible layer of accumulated material. Their roots, if they can be called that, penetrate further into the rock cracks, opening them wider. When mosses die and decompose, they add more organic matter. Bacteria and fungi arrive, beginning the extraordinary work of decomposition that will define healthy soil forever after. Slowly, over centuries, the layer deepens. More organisms arrive. Grasses, then flowering plants, then larger vegetation, each one contributing its roots to the loosening of the mineral layer and its dead tissue to the growing organic component. And with the plants come the animals, the earthworms and beetles and millipedes and mites and ants, and the extraordinary multitude of microscopic organisms that process and mix and aerate and enrich the soil in ways we are still discovering. A single teaspoon of healthy soil contains more microorganisms than there are people on Earth. Bacteria, fungi, protozoa, nematodes, an entire invisible ecosystem, cycling nutrients, decomposing organic matter, fixing atmospheric nitrogen into forms that plants can use, building the extraordinary chemical richness that makes fertile soil so different from crushed rock. Soil is not just a medium in which plants grow. It is a community, a living system of such complexity that soil scientists have spent careers studying a single square meter and still not fully understood everything happening within it. The formation of a single centimeter of mature topsoil takes approximately 100 to 1,000 years, depending on the climate and the parent rock. A meter of rich, deep agricultural soil represents, in some places, 10,000 years of slow biological and chemical work that began when the glaciers retreated and bare rock was first exposed to rain, and the first adventurous lichen soil carries the memory of the landscape above it and the rock below it simultaneously. The minerals in soil reflect the geology of the parent rock. Soils over limestone are different from soils over granite. Soils over volcanic basalt different again, each one colored and textured and chemically flavored by the rock from which it descended, and layered through that mineral memory is the biological memory, the accumulated organic matter of every living thing that has grown and died in that place, compressed and processed into the dark, rich humus that gives fertile soil its deep color and its extraordinary capacity to nourish new life. Soil is, in the most literal sense, the product of life feeding on death, generation after generation, building something richer and deeper with every passing century. The ancient and the new, the mineral and the organic, the geological and the biological, all of it woven together in that thin, quiet layer beneath your feet when you lie on grass on a warm day and feel the ground beneath you. That slight give, that faint warmth, that smell of something deep and green and old. You are feeling the accumulated work of thousands of years of quiet biological and geological patience. You are resting on something that took longer to make than all of recorded human history. And it is holding you now, as it has always held everything that rested upon it. Gently, without effort, the patient, living skin of the ancient earth. Breathe in slowly and let that patience settle through you like roots finding their way through dark, warm soil. Deeper, quieter, still. There is a world beneath the world, not the deep world of the mantle and the core that we visited earlier in our journey, not the world of iron and heat and crushing pressure miles below the surface. Something closer than that, something that begins just a few meters below the ground you walk on and extends downward and outward in a hidden geography of passages and chambers, and underground rivers, and lakes so still they have never felt a ripple of wind. The world of caves. Caves are among the most quietly extraordinary places on Earth. They are places where geology becomes architecture, where the patient work of water dissolving rock over hundreds of thousands of years produces spaces of breathtaking beauty, entirely hidden from the sky above, accessible only through the narrow openings where the underground world briefly meets the surface world. Most caves form in limestone, and the reason for this lies in the chemistry we have already touched upon in our journey tonight. Limestone is calcium carbonate, the compressed shells and skeletons of countless marine organisms accumulated on ancient seafloors over millions of years and slowly lithified into rock. And calcium carbonate has a particular vulnerability. It dissolves in weak acid. Rainwater, as it falls through the atmosphere and moves through the soil, absorbs carbon dioxide and becomes mildly acidic carbonic acid, the same gentle acidity that gives sparkling water its slight bite. When that weakly acidic water reaches limestone bedrock, it begins very slowly to dissolve it, not dramatically, just the quietest possible chemical reaction, eating away at the rock surface along cracks and joints, widening them by fractions of a millimeter over centuries, deepening them into passages over millennia. Given enough time, those passages become caves. A cave system is a map of water's patience. Every passage follows an ancient water route, a crack that was widened by centuries of dissolution, a joint that water found and followed downward until it broke through into open air below. The shapes of cave passages reflect the speed and direction of the water that carved them. Wide, rounded tubes were carved by water flowing full under pressure. Tall, narrow canyons were carved by water cutting downward more quickly than it widened. Broad, flat-ceilinged rooms formed where water spread out across a horizontal layer of particularly soluble rock and dissolved it evenly outward in all directions. The cave is the autobiography of the water that made it. every curve and hollow a record of flow. And once the water moves on, once the water table drops, and the cave passages are left empty and dry, something new begins, something that many people consider among the most beautiful things geology produces. The speleothems begin to grow. Speleothem is the scientific name for cave formations. The stalactites and stalagmites and flowstones and curtains and crystals that slowly, over thousands of years, decorate the walls and ceilings and floors of limestone caves. They form from the same chemistry, running in rivers. Water percolating down through the limestone above the cave dissolves calcium carbonate as it travels. When that water reaches the open air of the cave and a drop forms on the ceiling, it releases a tiny amount of carbon dioxide into the cave air, and as that carbon dioxide escapes, the water can no longer hold all of its dissolved calcium carbonate in solution. A microscopic ring of calcite precipitates out, deposited on the ceiling at the point where the drop hung. The next drop deposits another microscopic ring, and the next, and the next. Over thousands of years, those microscopic rings build into a stalactite, a slender, hollow tube of calcite hanging from the ceiling, growing downward at a rate of perhaps 1 centimeter every 100 years. The drop that falls from its tip lands on the cave floor below and deposits its own tiny contribution there, building a stalagmite upward to meet it. Given enough time, given tens or hundreds of thousands of years, the stalactite and stalagmite meet and merge into a single column of calcite from floor to ceiling, standing in the cave darkness like a quiet pillar in an underground cathedral. No architect designed it. No hand shaped it. Just water and chemistry and time. In Carlsbad Caverns in New Mexico, in Mammoth Cave in Kentucky, in the Waitomo Caves of New Zealand, in the Show Caves of the Slovenian Karst, in cave systems on every continent, these formations grow in their quiet darkness, indifferent to the world above, building their slow geometry in the absolute stillness of the underground. The air in a deep cave is among the stillest air on earth. No wind reaches the inner chambers. change of season disturbs the temperature, which remains constant year-round. A cool, steady, unwavering temperature that has not varied in centuries. The silence is total. No bird song, no traffic, no wind in trees. Just the faint sound of water dripping, echoing softly through the dark, and the slow breathing of the rock itself. People who have spent time deep in caves often describe the experience as profoundly peaceful. Something about the absolute dark, the perfect quiet, the constant cool temperature, and the sense of being held within solid stone produces a stillness in the mind that is difficult to find anywhere on the surface world. The cave asks nothing of you. It simply holds you in the quiet and the dark, while ancient water continues its patient work overhead. Let that image carry you now. The cave, dark and still and cool, the slow drip of water in the silence, the stalactite growing, one invisible layer at a time in the absolute peace of the underground. You are that still, that held, that quietly in the dark. And so we come, at last, to the end of our long journey. From the quiet drift of a nebula in the dark to the slow crystal growing in the deep, we have traveled through 4.5 billion years of this extraordinary world, through fire and rain and ice and stone, through the first breath of life in a warm ancient sea and the slow dance of continents across the face of the earth, through volcanoes breathing and rivers dreaming and mountains rising and falling in the long, unhurried rhythm of deep time, through fossils resting in their quiet stone and soil building itself grain by patient grain, and caves growing their slow cathedrals in the dark. It is a great story, perhaps the greatest story there is, and you have been part of it all along. The atoms in your body were forged in ancient stars. The iron in your blood settled billions of years ago to the core of a young planet. The water moving through you has fallen as rain on mountains that no longer exist, rested in oceans that no map has ever shown, traveled through the same great water cycle that has been running without pause since the first rains fell on cooling volcanic rock nearly 4 billion years ago. You are not separate from the earth story. You are woven into it, a thread in a fabric so old and so vast that no mind can hold it all at once. And yet here you are, a small and extraordinary part of it, breathing slowly in the dark. Let your breath slow now, even slower than before. There is no destination left tonight, nowhere further to travel. The journey is complete, and all that remains is the gentle settling, the way sediment settles through still water, drifting downward without any hurry, coming to rest in the quietest place it can find. You are already in the quietest place. Feel the bed beneath you. Feel the floor beneath the bed. Feel the earth beneath the floor, soil and stone and ancient rock, layer upon layer, reaching down through the geological record, through all the chapters we have visited together tonight, all the way to the warm iron heart of the world. You are resting on all of it, on the Hadean fire long since cooled, on the first ocean floor long since folded into mountain and plain, on the Archean rock where the first living things left their first quiet marks, on the sediment of 1,000 vanished seas, on the fossils of creatures that lived full lives in worlds you will never see, on crystals that grew in perfect darkness for 500,000 years, on soil that took 10,000 years to become what it is, just so that something could rest upon it, just so that you could rest upon it. Let the weight of all those layers hold you now, completely, without effort, the way the earth holds everything on its surface, not tightly, not forcefully, but simply and absolutely, the way gravity holds, the way stone holds, the way deep time holds everything inside it. Your body is heavy. Your thoughts are soft and slow, like silt drifting through the deep water of a still and ancient sea. Let every thought that surfaces simply drift. You don't need to follow it. You don't need to examine it. Just watch it rise and drift and dissolve, the way a wisp of steam rises from a warm stone after rain, curling once and then gone, leaving nothing behind but quiet. There is nothing to remember from tonight. Nothing to hold on to. Every word can drift away now, like dust drifting through the solar nebula before the Earth existed, weightless and slow, and utterly at peace. The rock beneath you is 4 billion years old. Whatever is on your mind is a few hours old at most. Let the rock win. Let the deep time carry it away, gently, the way a river carries a grain of sand. So slowly you will never feel it moving, but moving nonetheless, drifting away from you in the slow current, growing smaller and smaller until it is gone. And what remains is simply this: the breath, the quiet, the dark, the warmth. Breathe in slowly. Hold it for just a moment, and then let it go. Let it all go. Your shoulders can release now. Whatever they have been carrying today, they can set it down. The earth is broad enough and old enough and patient enough to carry it for you tonight. Your jaw can soften. Your hands can open just slightly, resting loose and warm at your sides. Your eyes, already closed, can let go of the last little tension behind them. That small, habitual readiness that the waking mind keeps always at the surface. It isn't needed now. Not here. Not tonight. The night is long. The earth is patient. And you are exactly where you are supposed to be, resting, breathing, drifting, held. Think for a moment of the cave. The deep, still, perfectly dark cave where no wind ever reaches and no season ever changes, where the air has been the same cool, constant temperature for centuries, where the only sound is the faint, slow drip of water building its patient formations in the dark, where time moves so slowly it feels inside the cave, like time has stopped entirely. You can rest in that cave now, not literally, but in the way the mind can go to a quiet place and stay there. Let the cave be the quality of this moment. The stillness, the dark, the perfect, unhurried quiet. The sense of being deep inside something ancient and solid and safe. There is nothing outside the cave that needs your attention tonight. There is only the drip of water, very faint and very slow, and your own breathing slower now. And the dark. Think of the crystals growing in that dark, atom by patient atom, each one settling into its perfect place in the lattice, silently, without effort, guided by nothing but the laws of chemistry and the gift of time. That is what sleep is, the mind and body finding their most natural, most ordered, most restful arrangement. Each thought settling into stillness, each muscle releasing toward its deepest rest, the whole extraordinary system of you returning to its baseline, its ground state, its oldest and most fundamental quiet. You don't need to do anything to make it happen. You only need to stop doing everything else. The crystals are growing in the dark. The continents are drifting, one slow centimeter at a time. The ocean is breathing its long tidal breath on every shore. The cave formations are building their silent cathedrals, one invisible layer at a time. The soil is resting between the rock and the sky. The fossils are dreaming in their stone. The rivers are carrying their patient cargo toward the sea. The mountains are standing in their ancient stillness. The deep earth is warm at its heart, slowly cooling, slowly turning. And the stars above you are the same stars whose dust became the ground beneath you 4.5 billion years ago. Everything is still. Everything is ancient. Everything is held. Everything is well. If sleep has not yet fully come, that is all right. There is no hurry here. There never was. Simply lie still and let the darkness be enough. Let the quiet be enough. Let the slow, even rhythm of your own breathing be enough. In and out, soft and steady, like the tide pulling gently at an ancient shore. You don't need to do anything with this feeling. You don't need to name it or hold it or understand it. Just let it rest with you, the way moonlight rests on still water, not asking anything, not going anywhere, simply present and soft and calm. The night is very long. The earth is very patient. And you are exactly where you are supposed to be. This is Sleepy Facts with Justin. Thank you for traveling through deep time tonight. Thank you for resting here in this beautiful and ancient world for a little while. Sleep now. The earth is holding you. It has always been holding you. It always will.